get load shed and the maintenance problems. But so he was thinking of doing that, but it's super expensive. Right? It's like you want a decent system that will be able to, you know, that you can live off reasonably normally. It's like, you know, 150, 200K minimum for a house, not less.
Yeah, I got a quote the other day because the ad that they put up on the internet seemed like it was quite reasonable because they said like you punch in what you normally spend a month on electricity between 1.5 and 2 or something. So I thought it would be like
It's like rent to own kind of stuff.
yeah, it would be like inexpensive, but it came back with more than 100,000.
I mean, I would also not go for the cheapest
Yeah. Keeping the option. No, I thought so.
Monitoring Twitter. So the socialist network in it. Apparently there's a little hidden option inside Gather that says global bold, so everybody can put stuff down, and that overrides all of the email addresses and it's on by default. So somebody now has tea or chai coffee stand next to their poster, which they will be allowed to keep. Sorry? Yeah, that's it. Now it's there. No. Well, it's a global poll, so they should not. Well, I hope there's no little hidden option to invite people.
Oh, but the reward creativity.
And as I said, they'll keep their coffee stand.
Well, you can add a funny sign to get together.
Yeah. Anyway, they're fun. Let's see. Living one.
Good morning, everyone. I'm given a responsibility of timekeeping for this session. So far, ADSS have been very nice, where we are having a fantastic talks. So this is first session of today is basically a focused demo. And first first demo of this session is like CASSIS and Aladdin interfaced for a VO compliant spectral data cube analysis tool. So now I would invite speakers to introduce them and proceed for the session. Thank you.
Yes, I am François Bonarel, and I am working at CDS. And I will, with the help of Audrey from Toulouse, show you a nice combination between Cassis and Aladdin. Can you see my screen?
Not yet.
Is it okay?
Yeah.
So this will be a recorded demo, but it's actually working. So if you go to the Aladdin page and pick up the Aladdin beta version, you should be able to reproduce what we will show you. So this is a collaborative work by all this bunch of people from Toulouse and Strasbourg. So let's first speak about the general astronomy context. As you know, we are now facing the production of more and more spectral cubes. In radio astronomy, for example, these spectral cubes are already huge. Surveys like ALMA, GIAP, VLA, LOFA, ASCAP, and so on are there and produce a great bunch of data. In the future, we will have SKA. Of course, I forgot MERCAT, sorry about that. So we also have MUSE and others in the optical range, optical domain, and even in the X-ray, XMM channel are producing tubes. The interesting thing is that archive data are available for reuse, sometimes on proprietary services, and sometimes also more and more with VO services. But we currently miss a VO tool to visualize and analyze these cubes. Be cautious that I know that there are these tools. We have seen a beautiful one yesterday, but it's not directly embedded as a VO portal. So that's my point. How to solve that issue? So Cassis and Aladdin are widely used VO tools at the moment on their niche. So the niche for Cassis is spectra and images in cubes for Aladdin. So our basic idea is not to create a new tool for spectral cubes, but to make Cassis and Aladdin collaborate by exchanging data and instruction in such a way that if you have a cube loaded in Aladdin, you select something, a region there, and you get the spectra and Cassis at that point. And if you select some range here, you will see the spectral plane in Aladdin. So Cassis, a little bit more about it. It has been developed in Toulouse by IRAP. It's a Java tool providing following functionalities. So first, you can discover spectra and access them from the SSA services or the EPNTAP services. You can, of course, display the spectrum. Cassis also allows line identification using either SQLite databases, local, or remote services, just as VMDC services or SLAB services from VO. So you can compare your spectrum with various models, fit them, and so on and so forth. And last but not least, determine physical parameters of the sources. Aladdin has been developed by CDS in Strasbourg. It's a Java VO portal with the following functionalities. So you can discover images and cubes either from data access layer services or from HIPS, and with the help of the so-called MOLP space-time coverage. All these are VO standards. You can overlay catalogs and database records on top of images at the right position. There are a lot of visualization features. Astrometric and photometric calibration are available. And the cubes can be displayed in movie mode. And you can also have some spectrum extraction from the cube. So the idea of Aladdin interface with Cassis is that Cassis is installed as a so-called plugin of Aladdin. It provides better integration than SAMP in such a way that you can share the same Java virtual machine and the memory buffers, and you can communicate instructions. So it works with fixed spectral cubes of whatever origin. So you can have your local cubes or preloaded cubes and work with them, but you can also access cubes via the so-called DAL services. And sometimes the HIPS cubes, which are not usable directly, they have the functionality to show their progenitors, which are HIPS cubes. So in that case, you can also load them and use the tool. So first, Aladdin can select positions or regions in the cube and extract compute spectra, and then send them to Cassis. The spectra can be deleted on whatever side, with the deletion reflected on the other side. You can also select channel ranges on the spectrum in Cassis and display store that on cube display by Aladdin. So now the demo, which is a recorded demo, will start with a local green bank telescope cube. And after that, I will show you a news cube retrieved from ESO-TAP service. So the first part of the demo, Audrey from Toulouse will speak.
Hi everybody, so welcome to the first part of this demo. So first we are going to start Aladdin. So for that, you open a terminal, you go to the right directory and you type java-jar aladdin-beta.jar. It opens an Aladdin window. And in this demo, I'm going to show you how to work with the local cube. So I go to File, Load Local File, and I select the cube that I want to analyze. To zoom in, you can click on the cube and use the middle mouse button. You can also use this cursor to zoom in or zoom out. You have another cursor here, and it is to move in the spectral dimension, so you can see that at least you can see the signal is partially right. And I'm going to show you how to visualize the spectra in Cassis. So for that, you go to Tools, New Tool, New Tool Controller. You click on Cassis, you install or reinstall it, and when it's done, you close it. Then you go to Tool, New Tool, Cassis Spectrum Analyzer. You have a welcome message, and another window with Cassis here. And then you can click on Spect, and you will see the spectrum for the corresponding pixel. So you can do it several times. Just overplot the spectra. You can change the color of the spectrum by clicking here. So, for example, I want some green color, and it also changes the color in Aladdin. If you want to delete the spectra, you can either delete it in Aladdin, so you select the position and you delete it. So it asks you if you want to remove the associated spectrum, so I say yes. You can also delete the spectrum in cases, so you click here. So I also say yes. And I'm also going to delete this one. There is also the possibility in Aladdin to select a circular area. So you can do it several times. And to do it exactly the same way. So, for example, in Aladdin and in Casis. You can also select your selection and move it, and you see that the spectrum evolves simultaneously. I'm going to choose the position where the lines are bright, for example here. So you can see 4 lines. So if you want, you can plot the moment zero map of a transition. So for that, you use the middle mouse button to bring it in Casis, and you have this map of the integrated flux on this line. So if you want to delete this map, you click on this thing and you delete it. So you have your cube back, so you can just bring it on it again. Sorry. And center it. If you want to remove this selection in Casis, you just need to double click. And you can see that if you click on the spectrum, you have the corresponding image in the cube in Aladdin. For example, here it's noisy. If I click here, the signal is much brighter. So now we are going to identify this line. So in Casis, you go to Species. So you have access here with a small database. So if you want, you can select a larger database. But for the example, it will be enough. So you select all the molecules and you display. So Casis proposes you 4 transitions. So there is 4 lines. There are 4 lines of CH3 CCH. And as you can see, it corresponds to these lines here. But there is a shift. So in fact, it's due to the velocity of the cube, because there is no value of velocity in this cube. So we want to determine the velocity of this source. So to do that, we can add a velocity axis. So you have to give reference frequency. So for that, you can read it here. So you can click on this transition. You click again on velocity and you put the same value. And hit enter. And now you have a velocity axis. So this transition here corresponds to this line. So you can zoom in and see that the velocity is about minus 6.1 kilometers per second. So if I display now a transition appears at the right velocity. You can do it for all the lines, and you can see that we clearly detected 4 lines of CH3CCH. So now I'm going to show you how to do a rotational diagram in Casis. So for that, you need to fit the lines. So there are different ways to do that in Casis. So for this demo, I'm going to show you how to use the advanced fit. So this window opens, and then you right-click on the transition, and you do fit CH3 CCH. So you can see 4 tables with some pre-entered parameters, and you can just select fit current, and you have a nice fit for the 4 lines. So you want to save this parameter, so you select the file. So it tells me that I didn't select the telescope, so I want to add one, so I select the DVT. And I create a new file, so I'm going to call it CH3CCH demo. So already file name like that, so I want to replace it. And I don't forget to save it. Then I go to rotational diagram, I load the file. It asks me a calibration error. So we are going to assume that it's 20%. I didn't compute the RMS, but it's something that you can do in Cassis if you want. And I convert to TSR and CMD for this view. And then I display the rotational diagram, so you can see that the rotational diagram is quite nice here. So with the middle mouse button, I select the 4 points. I close the selection, and I display the fit. It gives me an excitation temperature of 36 K and the column density of 1.5 times 14 per centimeter. So I'm going to stop here for the demo using a local file. And now François is going to show you the demo with the news tube decrease from the ISO tab service.
Yes, so suppose I am an astronomer interested in young stellar objects in the area of Orion Nebula, for example. So I give the name of a star there and display the DSS image of this area. And now I am looking for ESO services in this area. And I found in green a tab service. So I select the interface to this tab service. I am now defining the area where I will be looking for data. And I add another criterion, which is that I want cubes. So this is the OpScore data product type parameter, which I select to be cube. And then I would like to have only Muse data and not, for example, ALMA. So I select the OPS collection. So ESO tab service is sending me back the list of available data in this area. I go back again to my initial target, enlarge this, and I see that there is only one data set available. You have seen the field of view. I just check by looking at the OPS release date parameter that these data are public. So that's the case, 2021 January. So I go back to the data link menu. I discover that there is probably a preview in HTML. So I see there is a nice star in the middle. So back to the data link. The requested file, I know it's too large. So I select only the cutout facility, which we call the SODA in the SODA service from ESO. I selected, these cubes are 8 arcseconds by 8 arcseconds. I only took basically something like 2 arcseconds by 2 arcseconds in the middle. And I also selected a smaller spectral range than the full one. So I reduced by 100 nanometers on the blue side and 200 nanometers on the red side. So now it takes a little time, but this cube is coming. So now it is. So this cube can be displayed in movie mode. I can select some of the spectral planes or let that move alone. I can also change the contrast maybe. So this is typical Aladdin behavior. And then I can launch Cassis. As you have seen with Audrey, part of the demo previously. So I launch Cassis. So bring back the control panel there. And I just select the region around the central star. And this is the spectrum with 3 lines. So I directly see spectral lines, and I am selecting now the lines, as you have seen with Audrey previously. And these are N2 lines and the so-called H-alpha line, and again, the other N2 lines in the area. So basically, that's it. When you have done this, you can, of course, with these cubes that you retrieved from the VO, you are able to do exactly the same what Audrey has shown with the local cube. So you can play with that, it's online. Now, if you have questions, there are the main developers and the astronomers which have been collaborating in developing these tools are also online, so some of them can answer you.
Hello. Thanks a lot for this nice journey, though the sound in the recorded video is not very clear. But now we have time for questions. If we have, I mean, I cannot see any on Discord channel. Okay, there is one question from the room, please.
Hi, Francois. This is Igor.
Hello, Igor.
So, you know, I attended all the talks yesterday, and including the one from our group on the 3D visualization. And the main question, the main problem that we see here is that there are kind of 2 limiting cases. One case is when you download the entire thing on your computer and try to render it in the browser, which becomes awfully slow because the browsers are not meant to render the stuff. The other way is to produce the basically the visualization remotely and transfer only the images. And here I can see that you do the cutout of the data cube. So where is it done? That's my first question. On which end? And second, how do you deal with large data cubes? Because again, I can see here the limitation. Maybe it's not as severe as with browsers, because Aladdin and both Aladdin and Cassis know how to deal with large data sets. But still, downloading, if you want to play with the entire cube, even Muse is like 8 gigabytes, and so it's pretty hard.
Yes, you are right. So in the case of the cutout, I may not have been clear enough, but the cutout is a SODA service. So SODA is the protocol, the
So
VO
it's
protocol
on the
to
ISO
define.
side. So it's on the ISO side, right?
So yes, this is provided by ISO, and we are in Aladdin. We are just interfacing to this service.
Okay.
So the cutout is made by ISO, so we don't transfer the whole cube. The reason I use SODA is exactly what you said, because doing lively the retrieval of the 3 gigabytes of the full Muse cube will have been very slow. So if you want to work with the whole cube, you have to download probably previously and then play with it locally.
But this means that in order to play with it this way that you've shown, one needs to implement the SODA service on the server side to be able to do the cutouts. Is that right?
So this is intended that the archives implement not only the full retrieval but also the cutout. Yes, you are right. Mm-hmm. So we currently have a couple of archives in astronomy, which already have the SODA cutout facility. So there is ESO, but you can also find this at CADC, at GAVO, and at ASCAP, CASDA, things like that. So it exists already. Yeah.
And how about heaps? You mentioned heaps cubes, but you haven't shown anything.
So HIPS cubes currently we cannot have the collaboration between Cassis and Aladdin with HIPS cubes due to the fact that HIPS is loading extra information, so it would have been very slow. Okay. So the only way we can use HIPS is when HIPS show their progenitors. So that is the FITS file from which they have been produced as a link behind the HIPS. So if you have this, you can load them exactly like from a DAL service, data access layer service, OPSTAP or whatever, and it works.
Okay, thank you.
Thanks a lot.
Bye-bye, Igor.
So, do we have any other question from the room? Okay. We don't have any questions. So now we can say to next talk.
Talk about work I've done in collaboration with my colleagues John Good, Eva Dielman, Ryan Tanaka, and Karen Vahi.
Sorry for technical glitch. So, yeah. Okay. So next focus demo is to be given by Bruce. It will be about astronomical image processing of scale with Pegasus and Montage. So, I request Bruce. I think it's recorded, right? So this is a recorded video, and Bruce will be online, so he will be interacting with you, so you can ask questions. So now I would request the video to be played. Thank you.
I'm going to talk about work I've done in collaboration with my colleagues John Good, Eva Dielman, Ryan Tanaka, and Karen Vahi. So why are we giving this focus demo? Well, we want to show how astronomers can take advantage of only open source tools to build workflows that they can build, test, and execute on-premises machines and clusters, and then, as far as is possible, scale them without modification onto distributed parallel platforms such as clouds or HPC platforms. So what we're going to show is proof of concept, and we're here to get feedback on its value and how we can develop the project further in the future. The demo is freely available on a shared risk basis, and a little later on I will give you the link where you can go and access it. So the two tools we have chosen for this focus demo are the Pegasus Workflow Manager and the Montage Image Mosaic Engine. Now, both these tools are open source. They operate by design on multiple platforms. They both support Python APIs. They are, at least we think, reasonably easy to use, and they do play well with one another. So a schedule of events. To start off with, I will give a very short introduction to Pegasus and Montage. I'll spend most of the time on Pegasus since people at ADAS are probably less familiar with it than Montage, which I've spoken about probably too often at previous meetings. Then I'll give you the link to the demo if you want to sing along with it. And then we'll go to the main event, which is a guided walkthrough of the Jupyter Notebook by my colleague John Good. It'll show you how you can make images like this one on the right of M17, which is a 3-color mosaic made of 2 mass data. And finally, I'll describe what happens when we tried running this on the Open Science grid, and then I'll give you a summary of the demo. So to start, let me talk a little bit about the Pegasus Workflow Management System. It's a fully featured workflow management system. It allows scientists to develop portable science workflows using Python, Java, or R APIs. In this case, we'll be using the Python API. And these workflows are structured as directed acyclical graphs. Scientists can then use Pegasus to run their experiments on heterogeneous resources, including your local machine or local cluster, clouds, HPC systems, and computing grids. Now, Pegasus also provides monitoring and debugging capabilities via command line tools, or if you wish, a web dashboard. If one of your workflow jobs does fail, you can easily debug the problem with tools such as Pegasus Analyzer. Another great feature of Pegasus is that it automatically handles data movement between jobs. Whether you are pulling input data from an S3 bucket on the Amazon cloud or need one job's output to be sent to another job, Pegasus will handle this for you. And finally, Pegasus runs your workflows with data integrity and fault tolerance in mind. You can have Pegasus perform integrity checks on all files used in your workflow, and if jobs or file transfers fail, they can be automatically rerun. Alright, so when working with Pegasus, you'll typically have an experiment or a set of computations that need to be performed, and at a high level it will generally look like the drawing on the left. So you can then describe your abstract workflow programmatically using one of the APIs, in this case Python, as shown in the center image. And once that's done, your workflow will be serialized to a YAML representation, which will be consumed by Pegasus and compiled into an executable one meant specifically for your own execution environment. So once your workflow is compiled, it's ready to run. So at the bottom row on this chart shows some of the most common execution environments where users can run their workflows. It includes cloud resources such as AWS or the Google Cloud, HPC resources such as Xseed or local clusters, and even resources such as the Open Science Grid. So now I'll talk a little bit about Montage. It is an open source toolkit for assembling FITS images into custom mosaics. It's written in C because that provides performance and portability. We have deployed Python binary extensions of these C routines so that you can get compiled performance in a Python environment. Now the workflow in Montage is by design highly granular. There are separate modules written for each step in the mosaicing process, all the way from reprojection on the left and the chart on the bottom to co-addition at the right. And in the middle you have the background rectification steps. Background rectification simply means that you're rectifying the background of each of the images to a common level. In addition, this processing paradigm is embarrassingly parallel. You can process each of the images that you input into your workflow on independent machines, and you can use as many of these as you wish. So it's this granular workflow and this parallel processing that allows Montage to work very well with workflow managers. And in fact, we have used Montage with Pegasus before. For example, we built a 15 wavelength atlas of the plane of our galaxy in the infrared using purely resources on the Amazon cloud. So if you want to try out the demo, you can go to the link in the top right hand corner of this chart. We created a Docker image with everything you need to run the Montage workflow Jupyter Notebook. The Docker image contains an installation of Pegasus and HT Condor. Pegasus sits on top of HT Condor, which actually does the running of the jobs for you, the Montage binaries, and the workflow notebook. Now, shown on the right, you can interact with this container through Jupyter Notebooks via the browser. You can even use this container environment to test out different workflow configurations if you wish to do that. Finally, The container contains Pegasus tutorial notebooks if you want to learn more about how to develop your own Pegasus workflows for different applications. And now let's begin the demo. I will hand over to my colleague John Good.
With Montage, you can build arbitrarily large mosaics, and since large portions of the processing can be done in parallel, you have the potential to do in days or even hours what might otherwise take 6 months. Using cloud or cluster resources, it is now feasible to marshal tens or even hundreds of compute instances and tens of terabytes of storage for short enough periods of time that the overall cost can be kept reasonably low. But effectively using these resources can be a major task in itself, and building an infrastructure that can effectively switch between platforms even more so. That's where Pegasus and HT Condor come in. As we shall show here, it is straightforward to explain to Pegasus how to use your tools to do the processing you want done. Then Pegasus will work out an optimal processing plan in the form that can be handed off to HT Condor, and HT Condor already knows how to run such plans efficiently on all these resources and more. All we need for plan building are the Python libraries for Pegasus and Montage. Montage is used here just to gather metadata about the actual data needed for the mosaic. When HT Condor runs, it will use a separate copy of Montage on the compute resource in the form of a set of Linux executables. The free parameters for the mosaic are the location on the sky, size in degrees, and the dataset. For Pegasus to do its work, we need to populate 3 data structures. The first, the replica catalog, is information on the files that will be needed as input, where they are, and how to retrieve them. It is called a replica catalog because some datasets can have multiple available copies of the files, and Pegasus can improve throughput by alternately using different copies. The replica catalog doesn't need to track all the files that are created during the processing. Pegasus will handle those. The second structure is the transformations catalog. Transformations are all the tools that create new data from old, in other words, the Montage processing modules. Again, Pegasus is capable of keeping track of multiple copies of these tools, though in a case like this, they will just be executables in our local path. Finally, we have the workflow catalog, which keeps track of all the processing steps we define, the transformations used, and the specific files needed as input and created as output. All 3 of these catalogs are maintained as SQLite databases. We can populate the transformations catalog up front, simply by adding the paths to all the Montage modules we will use. The general flow for building a mosaic with Montage always uses the same set of steps, with variations depending on whether we need to reproject the images, which we almost always do, or correct the background levels. Even for properly flux-calibrated images, backgrounds can vary, especially in the infrared. The background there depends so much on where you are in the zodiacal dust cloud and what direction you are looking. The data taken over an extended period of time, here years, will have widely varying backgrounds. So, as we will describe below, we need to reproject all the images to a common frame, examine all the image-to-image overlaps to gather information on background differences, model a set of updates to the backgrounds that can minimize the residual differences, apply these updates, and co-add for a final mosaic. Our first steps are to define the WCS header for the mosaic we want to build and to search a remote metadata service to get a list of images we will need. Note we are not gathering the data now. The actual data downloads will be the first set of tasks in the workflow. It will be done when the workflow runs on the cloud. Various lists of files, the original data, projected images, difference images, background corrected images, will all be needed during the processing, and we can actually predict what these will be now. And so we can finally start building the workflow catalog. All the images listed in the original raw data table need to be added to the replica catalog. We don't need to explicitly call out a file download job for each one, as Pegasus will know how to get them and includes that step itself. We do have to define reprojection jobs for each image. We already calculated all of the image-to-image overlaps above, so now we can define the jobs that do that processing. In the workflow, these are set up so that they can be processed as soon as the reprojected images for each pair become available. So in the extreme case, where all the reprojections are done in parallel, as soon as the first potential difference pair complete, the difference job will start. While the reprojection and overlap difference fitting jobs can be massively parallel, the next steps for globally modeling the corrections focus down to a single thread. First, we combine all of the individual difference fits into a single table, and then we run the modeling code. This program iteratively estimates corrections for all the images and is optimized to be able to do this even with huge numbers of images in minutes. And while this processing does need to wait until all the reprojections and difference fittings are complete, those steps are fairly uniform in processing time, so will all tend to finish at about the same time. So in practice, this single thread step does not represent a bottleneck. Once we have the corrections, we can again spread the processing out and apply a background corrections in parallel. The final mosaicing step is, in this case, another focus point. However, for really large mosaics, we often find that in practice we prefer to co-add as a regular set of tiles rather than as a single image. Finally, we add in a couple of optional steps to create a fixed size PNG rendering of the mosaic. Remember that all of this was us explaining to Pegasus what we wanted done. At this point, we want Pegasus to work out an optimal processing plan based on our input. This diagram is a standard optional output from Pegasus showing the plan it came up with. Here, for a much smaller sky region, our graph gets ungainly with over an order of magnitude more difference nodes. The primary Pegasus processing in what follows is the line that reads workflow.plan submit equal true.wait, which means we want Pegasus to make the processing plan and submit it to the local HD Condor for processing. We also want it to wait for HD Condor to finish. For a serious run on the cloud, we would decouple all this, building the plan and then later submitting it to HD Condor on the cloud to run in background. Here Pegasus will monitor the HD Condor run and report progress in real time. We won't wait for that to finish. We could expand on this workflow to process all three bands needed to make a color composite at the end, or more likely would submit the processing as three workflows. We've done that here and made this composite. It's important to note that no knowledge of Pegasus needed to be added to the montage code for all this to work, and that is generally true for Pegasus processing. It is true that for typical montage processing, one would capture and analyze the response messages from the montage modules to control the flow. This allows you to react to the processing and add conditionals and loops. Pegasus is more basic than this. It only checks the program return statuses and for the existence of expected output files. And this is a mode that works fine for well-defined pipelines of the sort described here. So if you have a set of processing modules capable of being used in a pipeline mode where parallelization is feasible, Pegasus is a natural.
Well, having run the workflow on our local machines, we then went and ran it on the Open Science Grid. Now what we really wanted to do was run it on the Amazon cloud, but unfortunately we didn't have credits left, so we were not able to do that. The OSG is a good choice as a parallel platform because Pegasus works out of the box on the OSG Connect access point. We know this already, which makes it an ideal target for large workflows such as those provided by Montage. The Open Science Grid itself, or OSG as it's now known, is an NSF-funded project that facilitates access to high throughput computing. It is in fact free to use for any US-based researcher, and indeed in the past year it's provided over 1 billion CPU hours to researchers. Right, so what we did was we took our Montage workflow and ran it on OSG. It can be done with very minimal modifications to the Python workflow script. We did make several changes to take advantage of some OSG specific features. Well, first of all, we configured all the data movements to be handled by OSG's Stash Cache data infrastructure. Behind the scenes, the files are cached in an opportunistic manner that requires no extra effort on our part. Second, because compute resources are of various operating systems, and considering that we compiled Montage on Red Hat 7, in this case we wanted Montage to run on Red Hat 7 machines. We can achieve this by using RHEL 7 Singularity containers that are cached within OSG's CERN VM file system. So setting this up required us only to change a few lines in the workflow generation script. Now, on the right-hand side, we show some metrics that Pegasus reported about our run on OSG. First of all, the workflow consisted of 332 jobs altogether. Now, this number's greater than the amount of jobs we actually created in the workflow script because Pegasus adds in jobs to handle tasks such as data staging and cleanup. Next, there is the workflow wall time, which, believe it or not, is the workflow wall time. And after that, the next two metrics show cumulative job wall times. So as you can see, there's some queuing overhead associated with running things on OSG. For very large workflow runs, Pegasus does provide a feature called clustering, where you can cluster groups of tasks into a single job to avoid such overhead for such small independent jobs, which are precisely the kind of jobs that you have in a Montage workflow. In fact, the next step in this project is to actually use clustering to improve the performance of the workflow. Finally, well, we're happy to report that we have successfully run Pegasus on Montage on 2 platforms. Clustering of jobs on parallel platforms will certainly improve performance, and this is easy to do with Pegasus. Also, as our next step, we want to migrate this to the cloud. Pegasus will be especially useful in optimizing performance and costs. In fact, the Rubin Observatory has already used Pegasus in this fashion on the Google Cloud to study performance and cost optimizations. And finally, we invite everyone's comments and suggestions, and it remains for me to thank you all for attending and listening. Thank you.
Yeah, very nice, very fantastic session by the Bruce and team. So now we are open for questions and answers. So basically we have 3 questions on Discord, what I can see. The first one is like, how is code moved between systems, VM, containers, or something else?
Ordinarily, we do it with containers. It's simply the easiest way to do it, and it's the one we're most used to.
Okay, perfect. So there is another question, like, can you say a bit more about flow compatibilities? Did I hear basic, if then else are difficult? Can you comment? Yeah.
I'm sorry, I didn't quite
Okay.
catch that.
Okay.
Could
Can you say a bit more about the flow capabilities? It's a basic or it's a difficult? The question by Peter, or he can.
Oh.
Yeah.
I'm not quite sure what's being asked, so maybe I can get in touch with them later on. But generally, no, there's no, if I understand the question, there's really no great difficulty at all. In fact, it's very easy to manage the data flow. Pegasus was built that way to start with.
Okay, perfect.
And there's a very good description of this on the Pegasus website at ISI, pegasus.isi.edu.
Okay, so there is a very maybe it's a very naive question from me. Since this is using AWS services, so it's basically paid services. So can we have a freeware options of this? Like
actually, it was not run on AWS. The demo was run on a local laptop. It was a very small workflow just to show how it could be done in the time we had available on the Focus demo. And we moved it over to the OSG to show how it can run on a parallel platform. But the code is completely open. The container is available, and it should run perfectly well on AWS or any other cloud. So I invite people to try and do that. In fact, I'd love them to try and do it. And if they have problems or have comments, please get in touch with us. We'd love to hear from them.
Okay, thank you. So do we have any questions from the room? Okay, I don't see any. So anyway, we can keep the question and answer session in the Discord session, and we can move forward to next session. Thanks a lot again.
Thank you.
Yeah. So our next demo is about PyCPL and PyIsoRex, the ISO Common Pipeline Library in Python. It's by Anthony Horton and team. So now I invite team to share screen. Okay. Perfect. We can see the screen.
Right. Hello. Good morning, good afternoon, or good evening. I'm Anthony Horton from AAO at Macquarie University, and I'm here to talk about the CPL project. So before I dive into demonstrations, I'd just like to start with a bit of background. So firstly, for those who aren't familiar with it, what is CPL? So just quoting from the CPL webpage, the CPL is the Common Pipeline Library, comprising a set of ISO C libraries that provide a comprehensive, efficient, and robust software toolkit to develop astronomical data reduction tasks known as recipes. These data reduction tasks can then be executed manually by a user, or can be triggered in an automated data reduction framework known as pipelines, which are used at ESO to monitor the health status of VLT instruments for quick look data processing at the observatory and the creation of data products available from the ESO archive facility. So basically, CPL is the fundamental tool for building data reduction pipelines for ESO VLT instruments, and that has been the case since 2003 when CPL was released, and it's going to continue to be the basis for the ELT instrument pipelines. So these data reduction pipelines are built from recipes, which take the form of compiled shared object libraries, the .so files, and so each recipe performs one step in the data processing, or one task in the data processing. So it takes a list of input files, performs the task on them, and produces a set of output files. And then each recipe will have a set of parameters associated with it, that are used to control the processing. And then you can produce a pipeline by daisy chaining these recipes together. So this is supported by the functionality from the CPL library. So as well as the framework for creating recipes, you also have data types for representing images, masks, tables, matrices, property lists, and so on. There's a host of statistics, arithmetic and conversion operations for those data types. There are some higher level tools, for example, world coordinate system support, geometric transformations, wavelength calibration, and so on. There are tools for managing FITS files and other data access tools. There are some methods for integrating those data products into the ESO data flow system. And CPL also provides the basis for ESO's HDRL, the high-level algorithmic library that has more complex data reduction algorithms in it. At present, there are 3 existing tools for running these recipes. The first is Reflex, which is a graphical environment for running data reduction pipelines to reduce your data. There's Gasgano, which is primarily a graphical data file organization tool, but that also supports running these CPL recipes on the data. And finally, there is EsoRex, which is a command line utility for running CPL recipes. So briefly then, what is CPL? Well, PyCPL, sorry. CPL was developed in C for the usual reasons of efficiency and speed of execution, and it's well tested and understood. However, with the increasing popularity of Python for data reduction in astronomy, there's a need to provide access to CPL from a Python environment. And PyCPL is intended to do this in 2 ways. So the first is by making it possible to run existing CPL recipes, those that are written in C, from Python, and to access the results from Python as well. And secondly, to create new recipes directly in Python, making use of the functionality provided by the Common Pipeline Library. So when you take those together, then it becomes possible to develop a new pipeline in Python and to have those pipelines seamlessly combine existing CPL recipes with new Python recipes that leverage functionality from CPL, but also other scientific Python libraries such as NumPy, SciPy, AstroPy, Pandas, Matplotlib, etc. So interoperability is important there. One part of PyCPL is EsoRex, which is a new recipe execution tool that has both a command line interface intended as a replacement for EsoRex, does the same things, but it also, there's an object-oriented Python API that you can use from Python code or interactive Python sessions. And this tool can then run both classic CPL, C recipes, and PyCPL Python recipes. And then there's PyCPL library itself. So we have wrapped the CPL library with an idiomatic object-oriented Python interface. And we also have templates for producing Python recipes, which takes the form of a recipe base class. Just a couple of quick caveats about the demo today. PyCPL is currently in pre-beta. We're due to release a closed beta next week. So any details here are subject to change for general release. And also ESO standards currently require pipelines for ESO instruments to be implemented in CPL. So that's the way things are for now. However, PyCPL will soon be available as a way to rapidly prototype those pipelines in Python, as well as developing pipelines for other purposes. So I'll start with just quickly showing you the command line interface. So if any of you are familiar with EsoRex, you'll find this looks very familiar. So this is This is ESOREX, just displaying its various command line options. It's a very traditional command line tool. And PyESOREX is essentially the same. It's still in beta, so we don't have all of the options there, but it's exactly mirroring existing ESOREX functionality. And so, just as a very quick example, we can run PyESOREX, optionally providing it a config file, providing the name of a recipe. This one is from the BLT instrument Giraffes data direction pipeline. It generates master bias files, and we have to give it a soft file, and the soft file is just a list of input fits files, and we can then run this recipe, and we get some console output. It also generates log files and tells us that it combined 5 bias images and produced a master bias image. But I don't want to spend too much time on the command line interface. I'd like to move on to the Python interface. And so I have a notebook here that shows how this could be done in a interactive Python session, but of course you could equally do this in non-interactive Python code. So the process, you just have a few other imports to begin with, but you start by importing the PyESOREX class and then creating an instance of the class. So by default, when you create one of these, it will look for a config file in a default location. So there's a .pyesorex directory in your home directory. It looks for a pyesorex.rc file. And from that, in this case, it found one. If it doesn't, it will just use its default values. And you can then print the parameters that it gets from that config. This parameters property. And see here's a full list of parameters, including things like the recipe directory, where it looks for recipes, and some logging settings and so on. Alternatively, you can create a PyESOREX instance by specifying a config file at the start. And so in this case, I have a slightly different set of parameters. This includes a different recipe directory. You can also write config files. So this will either write the existing settings to a file, or with a optional argument, it'll write all the default settings to a new file. And you can read them as well. So having got your PyESOREX instance and it's configured to your liking, you need to load a recipe. Well, first you can list the available recipes. So let's have 2 methods. One was intended for a machine readable dictionary with a bunch of metadata. And there's also a more human-friendly text listing. It just lists here, these are the names of the recipes. These are all from the Giraffe instruments pipeline. And there's a synopsis here, just a short description of what they do. You then have to load it. There's a load recipe method. And then once you've loaded it, you can then look at the recipe parameters. So there's here, this recipe, the master dark recipe has quite a few of these. They can be various types. So some of these are options. They're basically enums, parameter enums. Others are just numeric values or string values. And you can also load recipes just by assigning to this recipe property. So I've loaded another one here. This is the Giraffe master bias recipe. And you see it has a different set of parameters. And these can be changed. So there's this recipe parameters property has an update method, and you can just pass in a Python dictionary of key value pairs, name value pairs, and then you can see this has changed the stacking method to median and set this bad pixel mask creation flag to false. Now the recipes can also use configuration files of their own. So we have a corresponding set of methods for writing and reading recipe configuration files. And these are all compatible with the ones used by EaserX. So if you have EaserX configuration files for recipes, you can use those in by EaserX. Having set up the recipe, then the next step is the soft file, and this is the file that has the details of the input fits files. So I have one here, which I can open. Not very interesting, it's just here. This is a very simple one. It's just a list of paths to fits files and then a tag. And this tag is marking all of these input files as bias streams. So then we can run the recipe and we get an output very similar to the command line. But having done that, we get a result returned. That result is a PyCPL object. It's a frame set, which contains frames. And each frame, in turn, has the details of an output fits file, along with some metadata for it. So we can have a look at that. So, for example, the first frame here has this path. It's tagged as a master bias. It's tagged as a data product rather than a raw or calibration file. It's tagged as final, and it's tagged as having the type image. Now, these frame objects, we have a method to open these as open the corresponding fits file directly as an AstroPy HDU list. So you can just straight away have a look at that. We've just got a single HDU in this list, primary HDU, and then we can quickly look at the header or the data as an NumPy array. Or alternatively, we can open the fits file as a AstroPy NDD data, CCD data object. More or less the same thing. And there it is. And we can then use matplotlib or whatever to take a quick look. And there's our master bias file. So that's running classic CPL recipes in C. So PyEaserX, of course, can also run recipes that are written in Python. So the process is almost exactly the same. We create a PyEaserX instance. In this case, I've used a different config file, and this one has two recipe directories in the config. This first one is where the giraffe pipeline recipes are, and this second file is a local file here, local directory here that has a couple of Python files in it containing some example recipes. So now, if we list the available recipes again, we have 3 additional recipes at the bottom, and these are Python recipes, but they're treated exactly the same as the classic CPL recipes as far as PyEaserX is concerned. So then we can load one, and this is a very simple hello world example called hello fits. And we can give it a soft file. We'll just use the same one again that has the giraffe bias frames in it, and we can run it. And this toy recipe just says hello to each of the fits files. So let's just have a look at how that's actually done from the recipe. So this is the Python file that contains the first 2 recipe examples. And here is the recipe we just run. It's a class. It derives from this PyRecipe base class. The first thing here, we have a set of class variables that have to be set. This is the metadata for the recipe. So name, author, copyright info, description, contact email, synopsis, and a version number. And the only other thing that's essential is to implement the run method. So this takes two arguments: a frame set, so that's the set of input files, well, the details of the input files, and settings, which is a Python dictionary of settings to apply to the recipe's parameters. In this case, this is a simple recipe, has no parameters, so we just ignore that, and we're just printing a greeting to each of the input files. And generally speaking, your recipes will have parameters instead. So I have a slightly more complex example here. Hello user, and when we load that one and print the recipe parameters property, we get this list here. So we see there's a username, an NFIT, and a reaction parameter. Now, if we look at the code, we can see how this is actually implemented on the Python side, of the recipe side. Again, we have these this metadata that we have to set. We have a run method, and in this case, we also override the init method, and here we create a self parameters attribute, which is a parameter list. This is one of the classes from PyCPL. It is just a simple container for parameters. And then we have three different parameter classes here that we create. So there's a parameter value, which is a simple value. And we have to set a name, context. In this case, that's just the name of the recipe, a description, and a default value. And the default value is also used to set the data type. So in this case, this is a string parameter. We also have a parameter range. Now this is like the value, except that it can only can be set to values in between a minimum and a maximum. This one is a integer parameter with a min of 1 and a max of 5, and a default of 30. And then finally, we have the enum parameters, parameter enum class, and these have a fixed set of possible values. Again, this is a string parameter with two possible values. And then we have a run method. This one does actually pass the settings as they come in. So it just iterates through trying to match keys from the dictionary to the names of parameters and setting the value. And then it prints some messages. So go back to the notebook and see what we get. So we get, again, it's a simple hello world type thing. Hello unknown user, nice to see you. And then a listing of the first three FITS file paths. And just like the CPL recipes, we can change some recipe parameters and then run the recipe again. It's slightly more personalized greeting. And we can write or read recipe config files, which have exactly the same format as the classic CPL recipes. Okay. So those are some toy examples. I'll dive a little bit more into PyCPL. So what is in PyCPL? Well, everything that's in CPL. So PyCPL is a wrapper around CPL. So all of the functionality that's in there is being bound to the Python API. Mostly in a very similar fashion, though in places we adjust the interface to make it more Pythonic. And there are 4 submodules to the library. So the first is core, and that's the one that has the classes for all the basic data types. So we have an image, mask, table, vector, bivector, matrix, and property classes. And those are all pretty rich classes. Things like image in particular have a lot of methods for doing arithmetic and logical operations and statistics and so on. We have some containers for these data types. So we have image list and property list. We have logging and console message system via this message class. we have error handling. So we have a set of custom Python exceptions, and errors generated from the CPL-C code are translated into Python exceptions, so they can be handled in the normal way. I'll show an example of that very soon. There's some statistics functions, and there's a polynomial class. The next module is TFS. That's for the ESO data flow system. So these are functions to ensure that the data products are compliant with ESO DFS standards. So you have things there that check the metadata and sign it with MD5 checksums and so on. Then we have the data reduction system, which has a few functions like simple object detection and aperture operations, detector characterization, fast Fourier transforms, some image alignment and stacking tools, nonlinear fitting, and WCS. And then finally, we have the UI module, this is the framework for building the recipes. So this is where we have recipe classes, C recipe and by recipe, frame and frame set for FITS file management, and the parameter classes, and a few more exceptions. So just to show you a slightly more substantial example, again, creating a 0x instance and setting an example file. This one is a little different. And just to show an example of a frame set being used here, we can just load that soft file and get the data. This is 3 raw object frames, a master dark file and a master flat file. And just showing some of the interoperability here, we can load that image, load one of these raw frames as a PyCPL image, and then we can pass that directly to matplotlib for display, because an image can be used in places where NumPy arrays are expected. And so we can see a raw image here with a lot of hot pixels. We can load our example recipe, which has a look at the description, run the recipe, which then processes our 3 raw files. It does a simple dark subtraction and flat fielding, and look at the results. We have a frame set with 3 frames in it, and we get the path to all those files. They're tagged as objects, they're tagged as data products, they're tagged as intermediate level and image type. And then we can have a look, again, just using the image class from PyCPL to load one of these files, and we get a nice picture of the galaxy. Then finally, just a quick demonstration of how the error handling is working. So this Python recipe, if you give it an inappropriate set of input files, in this case, give it just these bias frames, it can throw a PyCPL exception. So we have a custom exception for data not found, and this is all very familiar to Python. The interesting thing is that the same thing happens when errors are generated from the CPL code. So if one of the CPL functions generates an error code, it's translated to a Python exception. So here's an example where we try to create a mask object with a negative dimension, and the CPL error that's generated in the C code gets turned into a PyCPL illegal input error exception. And these being Python exceptions, you can do all the usual things. You can catch them, you can handle them, you can re-raise them. So here we catch that exception, print an error message using the messaging and logging system, and then re-raise the error. So that's it for what I want to show in the demonstration. If you'd like to know more, then there is a poster in room 1 on PyCPL using PyBind to bring Adaptive-C libraries to Python. So there's a bit more technical detail there and a discussion of some of the challenges of implementing this. Please do ask any members of the team any questions you do have. So I'll do my best to answer any questions on Discord or GatherTown for the rest of the week, depending on what you would like to ask. Though maybe ask somebody else in the team. So you can ask me about PyUserX or the Python API. Those are the areas that I've been most involved with. Or Anthony Heng about PyBind 11 and the C++ layer, which I didn't even really mention. Issues of memory management and error handling and so on. Nora Llorente about how we've managed this and scheduled it. Or Ralph Balzer or Lars London about the underlying CPL library or where this is all going. And just a reminder, I had a note on this at the start. These notebooks are on GitHub at this address if you would like to look at them a little bit more carefully. That's along with the example code as well. And I'll finish there. Thank you.
Okay, thanks a lot for a very informative demo of PyCPL. And now we have time for a couple of questions before we go for a break. And there are a couple of questions written in Discord channel. So I will take one for time being. What should C recipe writers already do now in order to make a potential shift to Python recipes in future easy?
Okay, that's an interesting question because yes, the way that it's all been set up, probably very little because PyCPL can run recipes written in C just exactly the same as it does in Python. So if you're writing C recipes now, you can use them in PyCPL as they are.
Okay, thank you. There is another, but I want to take it. The inclusion of DRS class in PyCPL means that it includes also SDRL tools, though it is already answered. So can you add statements on that?
Nuria says it there, indeed, yes. So we have not included any of HDRL in this, but yes, indeed, there are plans to do that as the logical next step once PyCPL has been done.
Okay, thank you, perfect. So do we have any other question here? No, I don't see any. I mean, these discussions are already being clarified by the team. So Peter is writing something. We can wait for a few seconds. Okay. Okay. Oh.
Stopped.
Yeah, I think it's gonna take time. So anyway, we can keep discussions on in the Discord channel. So thanks a lot, and thanks a lot to all the speakers of this morning session. And now we will break for coffee, and GatherTown will be open for posters. Thank you.
And we start with a presentation by Kirill Grishin, who will talk about observing, calibrating, and reducing near-infrared imaging mosaics.
Hello, I'm Kirill Grishin, PhD student at the University of Paris, and I'm also doing some research at Moscow State University. And today I want to tell you about our recent experience that we had with observing and reducing imaging mosaics in infrared with MIRS spectrograph on MMT observatory. And first of all, let's talk about main differences between obtaining images in optical bands and infrared bands. The main problem is that infrared detectors have a lot of imperfections and there are significant variations of sensitivity on small time scales, and also sensitivity depends highly on spectral content of light. The other problem comes from the high night sky background level, so you get very close to the saturation level even with 20 seconds of exposure time. The solution for the first problem is dithering. So you shift your image, you obtain a sequence of randomly shifted images and then analyze them one by one. The solution for the second problem is splitting whole exposures, long exposure into the smallest ones, and then also analyze them one by one. But when you need to observe extended objects, you need to obtain imaging data for several fields. And this is what I will be talking about in my talk. And here are some science cases of imaging mosaics in infrared, and you can do it for extended nebulas, for globular clusters, for even open clusters, for star, I would say star clusters, and for many other objects that fills a significant part of field of view, or even the fully fills field of view, field of instrumental view. But in my talk, I will focus more on the obtaining mosaics for galaxy clusters, and I will show you what we did for coma cluster. And as I said, in infrared bands, you need to do dithering. And dithering procedure, it's better to say that here's a shifting telescope, is a low-cost procedure for telescope time, because it takes much less time than, for example, changing positional angle of the instrument or the telescope. And this is the main reason why it's better to do joint dithering catalog for different nearby fields instead of doing dithering patterns for each field separately. But at the same time, if you plan to observe different fields at different positional angles, it's better to do fully separately, because, as I said, it takes a lot of time to change telescope positional angle. And this is what we did in our project. I want to say a little bit about our observational program, because we did infrared imaging follow-up campaign for multi-object spectroscopy data obtained with a newly designed and commissioned BioInspect spectrograph on MMT observatory. And on this image, you can see coma cluster rotated by 90 degrees. And green squares shows their positions and footprints of MIRS fields of view. And here you can see that we use only two position angles, 0 degree and -20 degrees. And we observe fields with different position angles separately in different nights. But fields with the same position angles are joined into a single dithering catalog. After we have obtained all the data, we need to reduce it. And we used ordinary standard Mills pipeline for this purpose, which includes such procedures like dark subtraction, flat fielding procedure, and also doing shifts in order to correct dithering pattern. But the last part of data reduction for infrared images is the most interesting part. This is the sky subtraction. There are two standard ways how to do sky subtraction for near-infrared imaging. The first way is when you use the same science frames to build the sky model for image and then subtract it from the science image during the reduction process. But it works very good for compact objects like stars, even if you have a lot of them in the field. But for our purposes, when you have a lot of galaxies, because we are working in the galaxy cluster, we are obtaining data for galaxy clusters, this algorithm leaves a lot of black holes, black rings around extended objects, extended galaxies, and this fully erases information information about the outer low surface brightness parts of the galaxies, and for our purposes, this is not the case because we need to know about extended dwarf elliptical galaxies or outer diffuse galaxies. We need to know about their outer parts. The second approach. The main idea of second approach is to use science images other from images you are reducing to construct a sky background model, and it works pretty well because it doesn't produce this over-subtraction artifacts like black holes or black rings, but at the same time it leaves a gradient, global pattern of sky background on the reduced image. And on the second row, you can see that there is a global gradient. Thank you. But this global gradient can be subtracted using global sky background subtraction algorithm, but it also produces black rings and black holes around the galaxies. But we did a different thing for this data set. We subtracted background from each frame in a stack by masking galaxies and other sources from the median image, from the median coordinate field, and by fitting the residuals, which is night sky background difference, by low-order polynomial. The main idea is to extract the gradient, which will vary very fast on the very small time scale. So here you can see the sequence for 1 hour image with 10 seconds between each frame. And this is the reason why we need to subtract background from each frame in a stack. And after this procedure, we applied this method to each frame in a stack. We collated all images in a stack, and here you can see how sky correction improves the global pattern of sky background. Okay, we have did some data reduction, but for doing imaging mosaics, we need to have accurate astrometric solution for our images. But the WCS, the initial WCS in reduced images comes from the telescope control system, and it is not accurate at all. It contains shifts and some rotation. And what we did, we did Levenberg Marquardt minimization for determination of best values of WCS parameters. And after this procedure, the last part needed for mosaic construction is the point determination. We need to do a FACS calibration. For these purposes, You simply match the catalog of sources on your frame with the reference catalog, and after this you do regression best fit minimization, where you derive the 0-point value. And when you have calibrated our astrometry part and both astrometry part and both photometry part for your image, you can build your mosaic. But for such a huge fields of view, for such huge mosaics, using the FITS file is not a good idea, because you need to deal with, when you are trying to analyze some objects, some maybe small galaxies, some stars, you need to deal with the whole image, with the whole data set of 12 gigabytes. And the best way to overcome this difficulty is to use HIPS survey, which can be viewed in our DIN. And this is what exactly we did. We put our data into HIPS survey, progressive survey, and you can analyze it now from our DIN Lite and from our DIN desktop. And here I just put some main points of my talk, some tips and tricks that can be used when you are obtaining imaging mosaics. And I hope that it will be useful for your research, and you'll be able to build another nice data sets, infrared imaging data sets for your targets. Thank you.
Thank you very much, Kirill, for that talk. I see no questions on the Discord channel, but are there any questions in this room? I don't see any either, so thank you very much indeed. Our second presentation in this session is by Emmanuel Coe and Antoine Boulanger, and it is about artificial intelligence for automatic identification of spectral lines.
Thanks to the organizer. Talk about artificial intelligence for automatic identification of spectral lines. The goal of this work is to provide to the astronomers some tools to automatically model astrophysical spectra using artificial intelligence. I show here, for example, a spectrum taken about 10 years ago. This kind of spectrum was made of a few dozen to a few hundreds of lines that could be analyzed with dedicated software like Cassis or XCLASS, which were interfaced with spectroscopic databases, allowing to manually identify the lines, as can be seen here, where each peak can be associated to species, molecule here, present in the spectroscopic database. Thanks to the increase of sensitivity and capabilities of modern instrumentation, nowadays the spectra can be made of thousands of lines, and making this manual identification more and more difficult. And even if this software also allows to compute synthetic spectra that help to identify the lines where the line can be important, that is the case in this spectrum, where you can recognize easily the brightest lines and identify them to the usual suspect species, as this was the case previously. The forest of faint lines, which are mostly coming from complex organic molecules, are much more difficult to be completely labeled. On top of that, data from interferometer, which produce a data cube with thousands of pixels, each of them having spectra made of thousands of channels that can be very different from one pixel to the other, makes this manual identification even more complex and maybe soon impossible. This will be even more true for future next generation of interferometer that will be soon in operation and will have even more capabilities. It is therefore clear that the astronomer needs to automatize the line identification, and artificial intelligence can help to fast up this line identification.
So we decided to build a convolutional neural network, which is one of the most used deep learning methods to realize classification of images or spectra. We tried two architectures, which are the one-dimension CNN and 2D CNN, that are almost the same. Indeed, both of them use the same hyperparameters, which are convolutional and fully connected layers, pooling layers. And the only difference is that the 1D CNN take vectorized input, whereas the 2D CNN take, as you can see in this example, input which are matrix. The idea is to feed the neural network with spectra made up of molecules and to train it to predict the presence or absence of these molecules. To achieve the classification task, we had to generate datasets, since there are not enough fully labeled spectra at each frequency range that astronomers would like to study. To do so, we decided to select only 10 to 15 species per dataset to make our prediction zone. Furthermore, we decided to select molecules that have a similar number of visible lines in the frequency range studied. That's because the convolutional and pooling operations tends to match the information of neighboring channels. And so if a species does only have 2 or 3 lines in the frequency range and other species have hundreds one, it could affect the prediction of the first molecule. Moreover, we wanted to have spectra as different as possible, so we decided to create them by selecting randomly several parameters, such as the number of molecules in it. And we decided to select also randomly several physical parameters, such as the temperature, the column density, the velocity local standard of rest, and the full width at half maximum. And this parameter just affects the intensity and the position of the lines. To perform the classification task, we decided to experiment mono-label and multi-label classification to compare them and to benefit from the advantages. We first tried the mono-label classification, which is the most common classification method. So in the first instance, we created one artificial neural network per molecule to test. And it may be a little bit slow and repetitive, but it's very helpful because it allowed us to set the layer-wise rate of propagation, which is an explaining artificial intelligence method. In fact, it allows us to discover which pixel is responsible for the decision made by the CNN. And without going into too much details, the RLP method just propagates the relevance that is contained in the upper layers to the lower ones. And it works just like the Kirchhoff law. So the information, the relevance present in a layer is equal to the relevance present in the upper and lower one. And to understand how it works, we have made one example of a synthetic spectra made up of methanol and other molecules. We displayed in orange the visible lines of only the methanol molecule. And on the lower image, we displayed the generated spectra again and the weights given by the LRP method. And we can see that the EVO weights correspond to the visible lines of methanol. So we can see that the CNN has made this prediction using mainly the methanol lines. Later, we built a multi-label classification CNN that return as output a vector of values between 0 to 1 that indicate the CNN prediction for all the molecules tested. and it permits to only train a unique artificial neural network, which is way more faster. To be sure to have the best prediction results, it's very important to set the good hyperparameter values. In our case, we try to optimize the value of 8 hyperparameters, such as the number of convolutional canals, the size of these convolutional canals, or the number of convolutional or fully connected layers, and so on. To do so, there are 3 main approaches that exist. The first one are the grid search and random search, that are the most used one, but they are not really efficient because the grid search tries all the combination possible. That is very time-consuming, and the random search only tries some combination selected randomly. That's why we decided to experiment the Bayesian optimization, and without going in-depth mathematics, it aims to maximize an acquisition function called, in our case, the expected improvement that you can see here, that tries to find the best compromise between exploitation, that means knowing that the neighbor of the selected set of hyperparameter gave great results, for instance here, and the exploration, which means a lack of information on this kind of set tested, for instance there. And this is this compromise between exploitation and exploration that allows Bayesian optimization not to be stuck in a local maximum. Moving forward, once the artificial neural network is trained, we want to test our real spectra to get the prediction on it. Since nowadays spectra are very rich and complex, we can pass it directly in our neural network. So we decided to perform some processing before. To do so, we used a dictionary, a Gaussian dictionary, containing the location of the visible lines for all the molecules that we want to test. And so we remove all the other lines. And once it's done, we rebuild the conserved line to give them a Gaussian shape, to make them look like the one from our training spectra. Once it's done, the real spectra has approximately the same complexities as the one we used to train our neural network, and we can use it to get the prediction on the molecule we want to test. When we look at our result, first with a test set using a K-fold validation, we can see that the accuracy of prediction are pretty close from each other and pretty good. But when we look at the result on a real spectra, which is rich and complex, we can see that the best prediction are for the molecules that have a large number of visible lines, like you can see here. But for molecules that just have 1 or maybe 2, 3 visible lines in the spectra, the prediction is give output pretty randomly with a high variance. And that's the result for the 2D CNN. And for the 1D CNN, we can see the same problem with a great prediction for this molecule with a large number of visible lines and pretty bad results for the molecule with a few visible lines. And these results comfort us in the idea that we have to generate data sets of molecules that have a similar number of visible lines. In a nutshell, we've seen that the identification of molecules in a spectra using artificial neural network is pretty promising. And if this work must be continued to achieve better results, it has already permitted to discover a new molecule in a star-forming region. This work will be pursued, and there are a lot of things to try, such as using other artificial intelligence methods, like other artificial neural network architecture or machine learning algorithm, to compare them with our existing solution. And thereafter, the objective is to expand our automatized solution to realize identification, not only on one spectra, but on hyperspectral cubes. And to achieve this goal, several approaches could be considered, such as spatial reasoning, spectral mixing, Another deep learning method, we could consider the UNet networks that give really great results on semantic segmentation of regions of interest. And that's all. Thank you for listening.
Thank you very much for that presentation. And I do see that Michelle is typing on Discord. And Michelle, if you are in the room, you might, of course, come to the microphone.
You guys make me feel short. It's not wrong. Hey guys, thanks very much for the talk. Sorry if this is a really naive question, because spectra is not my field. But if I understand correctly, you already have a pretty good model for the spectrum given a set of parameters, because otherwise you wouldn't be able to simulate it. I'm just trying to understand what's the advantage of using a CNN over like a standard Bayesian model fitting technique, for instance? Are they online?
Unfortunately, we are experiencing some technical difficulties, so I have to ask Michelle and everyone else who might have a question.
Put it on Discord.
To ask on Discord, please. Thank you. If there are no further questions, as I said, you have to ask on Discord. Let's thank the speakers again. Our third presentation in this session is by Vladislav Klotchkov, and he will talk to us about open source web tools for visualization of imaging and spectral data in RCS-ED v2.
Hi. So today I'm going to talk about technical background for web design tools, which are used for data and spectrum visualization in a second version of the reference catalog of Galaxy's SEDs. So firstly, a few words about the project as a whole. So the second reference catalog, second version of reference catalog of Galaxy SED is a project done by the Voxaster team, mainly based in Russia. And yesterday, my companion, Victoria Taptun, gave a wonderful talk on the harmonization of multi-wavelength photometry data for the website. And I also encourage you to check out our posters by my collaborators, the one by Vladimir Gorodjanov on spectral fitting, the one on K-corrections by Anastasia Kasparova, and Igor Chelagarian's poster on the project as a whole. So today I'm going to talk about the technical realization of the website, the tools which we use to create what we consider a quite neat user interface. So, well, as the name implies, there exists the first version of EarthSet, and it's also it's incredibly neat from a technological perspective, but the second version is, I believe, a bit neater. So the main difference between the two is what in the second version, we divided the website structure in two parts, front end and back end. So in brief, what it gives us, how it works is just back end sends the user-generated query to the main database, then processes the results with models and serializes, puts it into a JSON file, which then gets interactively displayed on the website, on the user side. So a bit later about the benefits of this approach. So the database engine is PostgreSQL with some add-ons, like we use PageSphere for fast code search, and also we have the access to a virtual observatory. I'm really sorry, but I believe you took the wrong version of my presentation. It's not the latest version. Okay, I might go on, but I don't have the presentation because you took the wrong version. I'm sorry, but it's not the one which is complete. Could you please turn on the right version? It has the prefix final. All right, I'm going to talk about the presentation now. So, let's start. Oh, okay.
Okay, let's have a short break while these technical issues are being sorted out.
No, it's fine. It's fine. No, it's okay. It's okay. I can do it. Is it this one?
Hold on.
Oh, wait.
Hang on. I'm good. I'm good.
Okay, and we can continue.
Okay, so hello, my name is Vladislav Klitschkov. Today I'm going to talk about the technical background. Oh yes, I'm going to talk about technical background of web design tools, which are used for imaging and spectral data visualization, the second version of reference catalogs of Galaxy's SEDs. So firstly, a few words about the project as a whole. The second version of ERTA-SET is a project done by VLOG-SASTA team, mainly based in Russia. And I also encourage you to check out some other posters done by my collaborators. Vladimir Garajanov's poster on spectral fitting, Anastasia Kasparov's poster on K corrections, and Igor Chingarin's poster on the project as a whole. And yesterday, our collaborator, Victoria Taptun, gave a wonderful talk on the data harmonization of multi-wavelength photometry data. So, and in my part, I'll be talking about the technical background and web interfaces, which I use for interactive data display. So, the main, so as the name suggests, we also have the first version of the website, which is I believe, also quite incredibly neat from technological perspective. But I believe the second one is a bit neater. And the main difference between the two, main change we implemented, was the division of the website structure in two parts, in front-end and back-end. So just in brief, I'm going to describe how it works. So there's this main database. The back-end sends a user-generated query to the database, gets the results, processes it with models and serializers, and then spits out the JSON file, which then can be now then interactively displayed on the user side by a JavaScript frontend. So as database engine, we use the PostgreSQL with some add-ons like QC3 add-on which allows us to perform the cone search, and the database has the VO access to a virtual observatory. The backend is made of a backend. Talking about backend structure, it's done with the Django Web Framework, Django REST API. And as I said, the main purpose of the background is to rightly generate the user submitted query, then process it to the database, then get the results, and then with models and serializers, put into the JSON file, which can be displayed. So, and we have one custom package for search queries. It's made by Ivan Katkov, who also gave his talk yesterday on IFU Visualizer. And you might actually have noticed what this visualizer, this website, has very similar technological structure as ours. And this also, I believe, to be one of the main points of my talk. The tools which we use are so incredibly extensible, so powerful, and so smooth and easy to learn, what you can build different websites for data visualization using the tools which I'm going to talk about in my talk. So what this custom query engine allows us to do is, apart from just a boring search by name or cone search, it also includes the logical operators in the search. So you can use all the logical operators and combine them in different ways. With, of course, the names, with the survey types, with a lot of different parameters. So here you can see the examples, some examples of the searches, like just a boring name by search by the object name, then some cone search, and then some logical statement. You can see it's quite intuitive. And I must say that this search query engine is immensely helpful in our research. And we even had some papers written by just fiddling with the search parameters. So it's incredible. We consider it to be incredibly powerful. Now, a bit about the front-end structure. So front-end was done using a combination of Vue.js and Quasar. So Quasar is responsible for the material part, and use the engine. And what we also consider to be quite awesome is the interactive plots, which we have on our website. So we have an interactive viewer for spectral energy distribution, which fully interactively gets its photometric data and displays it. And it's done with the Plotly JavaScript library, so it really has all its functionality. You can do whatever you want with it. You can zoom in, you can zoom out, you can squeeze it. It has flexible layout, and you can do whatever you want with it. And it's fully interactive, as I said. Then we also have the Baldwin-Phillips-Taylor-Revich diagrams. So I'm going to quickly explain what it is. It's just the diagrams which you use as a diagnostic for excitation mechanism to differentiate between different emission lines. So these diagrams, as I said, are also fully interactive. You can zoom in, you can zoom out, you can squeeze them, you can have them. And we also have the star formation lines and AGN lines added on them. And it has a flexible layout, quite a flexible layout. We also created an interactive spectrum viewer. So as literally everything else on the website, it has full interactivity. You can zoom, you can pan. And apart from that, it has different feed modes. So as I've said, we have fed about, I believe, 5.7 million spectral data with the N-burst algorithm. And you can, and these feed modes can be interactively displayed. We don't have that many feed modes yet, but we are going in the near future. We are currently actively working on it. You can see this button you can press and it will interactively display the feed mode. And currently we are working on displaying multiple feed modes. So you can just choose which one you want to represent. And as I said, it also has like full interactivity. When also, we have quite heavily customized the Aladdin Lite. So Aladdin Lite can be quite easily integrated into Vue.js framework. And so what we did with it, first of all, well, with default functionality, we added different multi-wavelength images so you can view the picture in different surveys. But we have also created, you can see these red circles. So all the objects and spectrums available on our website are available, are seen on this picture as red circles. And we also have created only click behavior for them. We made on-click behavior for them. So when you click on the circle, it's either if this is a spectrum belonging to the object, it will automatically scroll down to the spectrum. And if you will click on a spectrum object outside, an outside spectrum object, it will open a tab with its data. And with it, this customization also proved to be incredibly useful. So what are the main takeaways? So first of all, Django Web Framework yes, okay. So firstly, as I said, it turned out that Django Web Framework provides a really great interface for accessing data from Vue.js Observatory. And what I believe to really be the main point is what, as I said, we also have presented yesterday the IFU visualizer, which was basically done with the same technologies, completely the same technologies. And what I want to, the main point of my talk is that with the use of modern web frameworks, you can build apps with websites with great user interfaces for your research purposes. And today it's easier than ever because it's my personal experience, but Vue it's quite easy to learn. You will need a lot of front-end programmer background to enter it. So we also, of course, encourage you to use the second version of reference catalogs, Galaxy SCDs, in your research purposes. And as I've said, website still undergoes a very active phase of development. So we encourage you to, of course, visit our website and send your feedbacks, or maybe write some bug wrappers, because the website is still in development. So thank you for your attention.
Thank you very much indeed for that interesting talk. And we have one question on this talk so far, which is, can the SCD and the Spectre Viewer tools also be used on their own? And what do they take as input?
Excuse me, can you please repeat?
Yes, sorry, of course. Can the SCD and the Spectre Viewer tools also be used on their own? And what do they take as input?
Well, no. Actually, the elements were kind of are all embedded in one structure. So as an input, the spectral viewer takes the data it gets from the backend. So they don't have like an IP written for it, so just to give it the custom data. It can display on the data it gets from backend, and so it's just embedded in the website structure. And on its own, I don't believe it will work. It just can't work.
Thank you. We have a second question from Matthias, also on this talk. Did you have to apply any on-the-fly optimizations, like scrunching for Plotly, when using larger data sets? From my experience, 5,000 points is getting close to the limit of smooth usability. or do you not reach that level of data size?
When it comes to Plotly, we don't really have that much data visualized by Plotly. We have the BPT diagrams, but we don't just plot the dots. We have a different mechanism for plotting the background of it. And apart from that, for a spectrum, I don't know. We did not really have problems with data visualization with Plotly, having problems with visualizing large parts of data, because I think SpectraViewer works just fine.
Thank you, and I think we have time for one more question on this talk from Sarah White, who says, very cool, are there plans to extend the SED plots into radio bands? In which case, how would you cope with multi-component radio sources?
Currently we might do it, but currently I don't really think we have plans to extend it into radio spectrum. But we might do it in the near future, in some future.
Thank you. Are there any questions in this room? I don't see any, so thank you very much again. And our fourth presentation is by Raoul Infant-Sens, who will talk about managing data lineage for archivable reproducibility.
Hello, do you hear me? Is everything fine?
Yes, we hear you. Thank you.
Yes, great. Sorry, that was just a problem in the web page. I'm Mohammed presenting, so Raoul is my co-author.
My apologies.
Yeah, it was a problem this morning in the web page. Sorry. Okay, so I'll just share my screen, and everything should be ready. So is the screen up now?
Yes.
Perfect. So thank you very much, everyone, for coming. So today I'll be talking about manage, in line with the first topic of this ADASS, managing workflows and reproducibility. In parallel, we have as you all know, the Discord channel that you can see here. I've already put some links. The slides are already on Discord channel. Please feel free to ask any questions during the talk. Of course, I'm talking now, but after the talk, I'll be very happy to answer them. Okay, so the basic idea behind, when we talk about pipelines, the most generic idea of a pipeline, what is it? It's just we have software, we have data, like our data come from a telescope, we have some software, we build the software, we run the software on the data, and boom, we have our paper or data release, right? And this is a very high-level view of a workflow, right? But in the process, there's many questions that we can, if we just take these steps and ignore these questions or don't try to answer them properly, the validity of our final result really goes into question, because many things behind the scenes are very important. And this is a really important problem both in the sciences and in the data analysis world, that we have, that it's very important to keep a lineage of the data and the software, and of course the data, the processing, and the final reduced data. And this is a very well-known problem in the community. There was this paper in 2016 which has become famous. It's Nature had asked like 1,500 people that are published in Nature before, that is there a reproducible crisis? And you see only 10% say no. 52% say yes, there is a significant crisis, and 38% say there is a crisis, but it's not too significant. This is from all the fields, it's not just astronomy. So since time is limited, I'll just jump directly to the method. And of course, there's a full paper on this, and this is the link here. It was published a few months ago in Computing and Science and Engineering, and it's also available on archives. The basic idea is that when we look at this plot here, the basic problem that most people fall into is that science is kind of driven, we feel that science is driven by its results. However, science is defined by its method, not its results. The method of obtaining the result is defines the result and the validity of the result. It's not the result itself. So how do we teach this? Now, this is a very technical, philosophical, let's say, point, but let's get to a more concrete set of things. How do we define this method and that a scientist's result should be defined by? Okay, so we're talking about the computational science here. So, laboratory work or going to the observatory is not in the scope of this discussion, because they are before data comes into a computer. So the moment the file or data comes from a telescope or microscope or I don't know, whatever real world instrument we have, the moment it's stored as a file, we're talking from after that, not about like how to obtain data in a replicable way. Okay, so so these are the set of premises that we as time, while we were working on this, came up for us. And one of the first ones is that the project should be complete. So effectively, it should only rely on a minimal Unix-like system, which can be named the POSIX, is commonly known as a minimal system. It shouldn't require root access. It should be able to run non-interactively, because human intervention means incompleteness, right? At the moment a human comes in, reproducibility comes out. Should be done without without internet connection, should be used, so it should be doable without internet. So all the components of the analysis should be able to be kept on one computer, as far as like the volume and things allow. Okay, it should be modular. It should be in plain text, because now this is an important thing that I'll touch upon in a few slides later as well. But it's very important that the project be in plain text, because binary formats need special software, and those software are going to be depreciated. The plain text is not. ASCII or Unicode are not going to be depreciated in the foreseeable future. However, if you have a Docker file, Docker version XY, it's not going to support that version anymore in like 10 years. Or if you have, I don't know, some binary format anywhere. So that the project should be plain text. It will also allow version control. It should be minimally complex. The inputs and outputs should be automatically verifiable. And finally, of course, it should all be free and open source software. If it's not free, I would argue it's not reproducible. Okay, so let's get to our solution. So that was the principles that we've been working on, that are the founding basis for this method. So let's get to the first set of questions about the software and how you build them. So as we said, this whole project, this whole method, manage, we call it managing data lineage. So we've merged the manage and lineage together to make manage. So in manage, everything is plain text. Everything is plain text. Nothing is from is any other format. And so over here in the next few slides, I'll just show in a tiny text editor that you can see some aspects of what I'm talking about. So in the part about software building and the necessary environment, in manage, initially we were thinking of just using like the operating system package managers or things like Conda, but they have a big problem because they're third party to the project. So they're not if you want, so for example, this is like Conda on GNU-Astro on Conda. You see the web page here. So look, for example, these are version 16, right? For version 16 of GNU-Astro that just came a few weeks ago, there's already 2 versions on Conda, because after we released version 16, CFITS.io, which is the dependency of GNU-Astro, was updated. So if you just run Conda activate GNU-Astro, you're going to get a different version of built GNU-Astro. And it is possible within Conda to keep these dependencies and use this hash to identify it. But to be honest, I haven't seen it used too much in many papers that work on reproducibility. And also the operating system. So for example, many people go to Docker, but then or containers. But then, for example, in Docker, when you say from Ubuntu, for example, you want to, in your Docker file, you want to start your operating system. So say you want a relatively older, let's say stable operating system, like say from Ubuntu 16.04 that came in April 2016. If you include this line in your Docker file, and only this line, it even includes the version of Ubuntu. Now click on this. This is where the ISO image comes from. Look, the dates are 2021, just this month, right? It just came like 2 months ago, and these are the latest versions. So even when you just run a simple, when you give the version of the operating system, you're going to get a different base operating system every time. It's going to have different changes. It's changes, and it's really important to understand that these create those low-level things that change every time you create a new Docker image or run the Conda file. Unless you have everything under control, which is possible, but because it's third party to the research project and the pipeline and workflow, it's usually very hard. So in Manage, we just decided to include the build instructions for all the necessary software of our project inside the project. So for example, this is the dependency tree of Matplotlib. Just look at all the dependencies. So we have versions of, we have the instructions, for example, of Matplotlib is inside Manage. So you see it builds everything within the plain text, with plain text files that are managed with Make. So it builds the full software environment all the way from the high-level science software. So for example, over here, I've highlighted like Python, AstroPy, or GNU Astro. And you can see like it has these versions. And from the high-level science software, it goes all the way down to even building the C compiler. That is the core of all the software in your project. So besides the C compiler, it also builds LS, CP, make the, everything. It even builds LaTeX, which we need for the paper. It doesn't need root permission, so you just give one directory, and it will take like usually 1.5 to 2 hours to build everything from source. And the thing is that even the tarballs necessary to build the software, we have our own separate repository for it that's just opening up right now. It's on Zenodo, which is managed by CERN. And so all of the tarballs that are necessary in a managed project are actually archived here. Then because we build the software and because we're scientists, because all the package managers are usually created by non-scientists, they're like software engineers, we actually include the citation of the software within the project. So because the ultimate goal of a science, let's say pipeline workflow is to create a paper, is to create a report of a data release or something. So you see over here, we have in this paragraph is created automatically by Manage as a LaTeX macro that includes the citations to all the necessary software. So as the author, you don't have to worry about not forgetting to cite. And then, okay, so now we're coming to the third branch, which is data. So for data, we include the full URL of every input data that's necessary and an MD5 checksum that will check the input data as it gets downloaded or if it's already available on the computer. Then for running the project, so Manage is fully, let's say the workflow is managed in Make because we want long-term reproducibility, right? We don't want the fancy tool that came out yesterday and is going to be depreciated 2 days later. We want that like in 40 years, we can open this and run it. And the only thing that is guaranteed to stay for 40 years is Make. Because the whole operating system that we use today is built with Make. And it's been here for 40 years and it's going to stay until a revolution happens in computing that changes our operating system. And in Make, managing dependencies is very easy because in Make, you see, you have the full command as a simple plain text file and you just define dependencies. And from those dependencies, a nice workflow is created and only things that are necessary to be built or run. And finally, the report or paper. So for the report and paper, I'm showing this tiny paragraph from the Noyce Chisel paper as part of GNU Astro that we had a tutorial a few days ago. So in this paper, have a look, these numbers in the PDF of the paper, in the LaTeX source, they're not numbers. They're LaTeX macros. And then these LaTeX macros come from this file that contains all of these macros, the numbers. And then these numbers are generated at the same processing phase that the process, the analysis that we report in the paper or data release report was done. And you see, so we're able to, anytime something in the analysis changes, the paper will be automatically updated. So as an example, I will just reproduce this tiny plot from a paper that worked on counting how many papers cite software. And so just as a tiny workflow, I'll just show the whole structure of Manage. So the whole, because it's in Make, it's good to see everything from the reverse, from the end to the start. So look, we have paper PDF is, the final goal of any research project, right? So paper PDF, you see the green boxes are files that the user has written with their hand. And the blue boxes are files that are created by Manage, which includes LaTeX and everything. So this project.tex is the file that I showed with all the numbers. Before we go into building the paper, everything is verified in this verify.mk. Everything is reserved with a checksum the moment we publish a result. And then, so the things that come into verify, so for example, I was showing a plot. You see the input data for the plot. They're from this, their plain text table. This plain text table comes from here. This comes from here. And this input.conf has the URL and checksum of the input. So you see, we have the full lineage of how the URL of the input turned into paper.tex. And with all the full analysis, and this can easily be expandable with Make, you know, and because something like the Linux kernel, GCC is built with Make. I mean, that's larger than any scientific project. It's easily expandable. And finally, because everything is in plain text, you can manage it with Git. So for example, you see we have all of the answers to these as a Git project. So today and tomorrow you update your project, and this is how manage is defined. Manage is actually a Git branch. So you branch off your project here. So you want to start your project today. You branch off from Git, from the main branch. You start to do commits in your project behind the scenes. The infrastructure and manage that contains like the low-level software instructions and things gets updated from user inputs. And then you can always merge your system. And then when you make your data release, you can in fact verify it. You can include the hash in your paper, like these two papers here. Look, we finished the abstract with the hash of the manage commit that we done this paper with. So then you can publish these everywhere. So for example, this is the Managed Papers archive repository. So you can just come here, go to other formats. Because it's just plain text, it's only 100 kilobytes. It's less than one figure in your paper or data release report. And then you can just come to download source. Look, I'm showing it here. And then you can just look. We have everything effectively here. Look, the full software in archive. We have how the instructions of how GCC was built for this project, how AstroPy was built for this project, including, of course, the LaTeX and the high-level analysis also. It's all here. And besides archive, you can also put it on Zenodo or Software Heritage. Software Heritage is a huge project which is collaborating with UNESCO for archiving human software heritage. And you can actually have all of this thing in one package to answer. So as a final slide, you can see that I'm just showing the future prospects. You see that it's great for researchers in other fields or PhD students to exactly see how you've done something, to verify, to test incrementally, to do machine learning. So like, for example, if you have hundreds of pipelines like this, that are on Galaxy Evolution, you can use machine learning to find the best data set, the best analysis method, the best software versions to make a certain research project. And finally, so we got a grant from RDA 2 years ago, and it was also highlighted in Nature Astronomy with a really nice name, no expiration date. Please read this paper. It's like a public referee report. We had no idea that they wrote this, and then suddenly when this came out, and it was interesting. Okay, thank you. I'll leave you with these slides.
I do not see, thank you very much for the presentation, of course. I do not see any questions on this talk, but there are two comments so far. And the first one is from Dirk Petri, who says, interestingly, the way the ALMA Observatory is delivering its data products implements in a way what you are suggesting. We deliver the original raw data with a recipe to turn it into calibrated data and images. This was originally done to save archive space, but it also gives the user total reproducibility. And the second comment, very sweet and short from Specicia, is, this is incredible. And then Michel goes on to say that all we need is a machine learning step to write our papers completely automatically.
Exactly, because you can even blend in natural language processing into this. Because it's all in LaTeX macros, all the numbers directly link to the analysis command. Just imagine your English grammar gets mixed with the Python command that you used. It's exactly. That is really something I'd like to work with someone on natural language processing and machine learning. To automatically construct sentences from a Python command, for example, or a shell command or something. Exactly.
I see no further questions on Discord. Are there any questions in the room? Doesn't seem to be the case, so thank you very much again for your presentation.
Thank you very much for organizing. Bye-bye.
We conclude this session with our second poster lightning talk session, which will last about 20 minutes. But before doing that, let us thank all the speakers of the session again, please.
For the past 30 years, Atarayo has been processing its single-dish continuum data using an all-command line program called Lines. Lines, unfortunately, has not been maintained for over 7 years. It's based on Fortran 77 and suffers from compatibility issues with some newer operating systems. It requires expert installation, and users are required to manually set up plotting parameters as well as perform raw file conversions each time they run a new analysis. DRAN, the Data Reduction and Analysis Program, was developed to address these and other similar issues inherent in the Lines program. The new program is fully automated and also allows for single-file and user-led or manual operations. It has a user-friendly command line and graphical user interface. It's based on Python and also offers a range of new features like outlier detection and flagging, which were not previously available with Lines. Comparing results obtained using DRAN to those obtained using Lines shows that the two softwares are comparable, and also that DRAN seems to appear to have smaller errors in its fitting routines, implying that it may even be slightly better than the old Lines program, which was one of the goals we wanted to achieve with the new software upgrade. Thank you for your time.
Hi everybody, my name is Tamara Rivera and I am Scientific Database and Web Access Engineer at CEFCA. CEFCA is carrying out from the Observatorio Astrofísico de Javalambre in mainland Spain two unique multi-val photometric large sky surveys, JPAS and JPLAS. The two large surveys include quadrilateral and individual frame images and catalog data. To publish all of this data, the CEFCA Catalogs portal has been implemented, offering web user interface services as well as virtual observatory services. This contribution summarizes the effort and work made in the CEFCA Catalogs portal to enhance data publication following fair principles, increasing data value and maximizing research efficiency. For example, to make data findable, the CEFCA Catalogs publishing registry has been implemented. To improve accessibility and interoperability, all service data is accessible through BO services which have been validated using EBOA validators and improved to be full compliant. And to improve the usability and provenance information, individual frame images are now offered. But there is still work to do, so we are going to continue working to be more fair.
Concept behind the idea of our plugin: get closer to the realization of three-dimensional sky maps. Three-dimensional information, such as conditional and marginal distance probabilities, are provided for any position of gravitational wave sky maps. As you can see from the video below, for any gravitational wave sky map visible on Aladdin, several SAM connections are set to receive an M-type about the coordinates of the click position of the map, of which the probability distributions along a line of sight are embedded in a tkinter interactive window. Thank you for listening.
Hi, my name is Ulrich Amen Busop. I am a postdoctoral fellow at Zurich University. My poster is about accelerating the search of optimal solution intervals using Dask arrays. So what are solution intervals? In most calibration softwares, the user has to set a time and frequency interval for which he assumes the gains are constant. This helps improve the signal-to-noise ratio and better constrain the optimization process. The difficulty is selecting the right solution interval. That is one that's long enough to provide a good signal-to-noise ratio, but at the same time short enough that you can subtract the intrinsic variations in the gains. In our previous research, we found out that in order to have optimal solution intervals, we need to compute them separately per antenna, frequency channel, and data chunks. In this poster, I discuss how this computation can be accelerated using dask arrays and XArray-MS. See you during the poster session and have a good conference.
Hi, my name is Sándor Kunsági Máté and I am a PhD student from Hungary. In our work, we have developed a two-step source separation tool where we can successfully decompose simulated disk galaxies into the young blue and old red stellar populations. We have created a neural network that predicts the two broadband spectral energy distributions, or SEDs, from the color distribution of the galaxy within a mask. The achieved accuracy is 2 to 3%, which is about 2 to 4 times better than using Scarlett. We then implemented the model of galaxy image generation in TensorFlow and optimized this model for the morphology matrices while fixing the S-series. As you can see, this very simple model provided better predictions for the brightness profiles than using Scarlett. If you have any questions, feel free to ask me.
Well, hello everyone. My name is Landman and I work in the radio astronomy research group at SAREO. My research mainly focuses on improving imaging and calibration algorithms for continuum interferometric data processing. In this edition, I'll be talking about PFP-Clean, a distributed imaging library I've been developing in Python. Come and talk to me if you're interested in fast and accurate distributed gridding, or, as my poster title suggests, if you want to know how to use the preconditioned forward-backward algorithm to tidy up after clean. Hope to see at least some of you at my poster. Cheers for now.
My name is Mark Taylor. I have a poster X7008 about a program called TAPLint, which is a TAP validator. I'll run it while I'm talking. TAP, the table access protocol, is a VO protocol which is used for clients to talk in a standardized way to remote databases. It's a complicated beast. It's composed of a dozen or so standards. And so if you're implementing a TAP service, then there are lots of opportunities to get things wrong. TAPLint is a tool which will act as a client and pose lots of queries to the service and check that the responses it gets back are in accordance with the various standards. This is it running, and you can see it just outputs lots of different reports. W means warning. There's something that you maybe should take a look at. Info just tells you what it's doing at the moment, and if there's an E, it's an error that means something's in contravention of the standards. If you're running a TAP service, try running TAPLint against it and see if it's behaving correctly. Thanks.
I want to give you a very brief summary of this poster. This work is part of the post-processing data being carried out in Wallaby Survey, where different centers in different geographical locations, such as Australian SRC, Spanish SRC, and CIRADA in Canada, will produce advanced data products publicly in the forum source catalogs, cutouts, or kinematics that have to be replicated in an effective way. Here we develop a model and a strategy to solve this data distribution problem. We validated several services and tools, but finally we decided to use Bucardo as a replication engine. To validate the effectivity, a benchmark has been designed to simulate the production of data and its distribution to the sites, capturing the metrics. The results are clear. Data synchronization and replication is sufficient for the future scalability and remote collaboration needs between sites. That's all. Thanks. Bye-bye.
Hi, my name is Evan Jones. I'm a graduate student at UCLA working with my advisor, Tuan Do, and I want to share with you the data collection process for our project performing photo Z estimation with galaxy images using a convolutional neural network. We use data from HSC to obtain 5-band photometry for galaxies spanning up to and beyond redshift of 4. Cross-match these galaxies with available spectroscopic redshifts, and then input this sample into HSC's image database to obtain images in each of the 5 bands for about 300,000 galaxies. We then process each of these images in Source Extractor to remove background objects from the field and perform a number of quality cuts to finally obtain a data set of about 220,000 galaxies for input into the neural network.
Hello everyone, my name is Jan Grange and today I will be discussing poster X9002. This poster is based on work we did in the ESCAPE project for Work Package 2. The goal of this work package is to assess whether the infrastructure that is used for data management by some of the particle physics experiments can also be applied to other fields like ours. I will first start by discussing the infrastructure itself, which consists of three tools. Ruscio, which takes care of data management and application of rules and policies. FTS, which actually takes care of copying the data between two endpoints, and IM, which gives users the opportunity to log in to the system using their institutional credentials. Furthermore, I will continue by discussing some of the differences between our fields, what makes astronomy special for data management. If you want to know more about this, please come to me during the coffee break or have a look at poster X9002.
Hello and welcome to poster X9-005, using script generators for pipeline prototyping. In this poster, I am presenting a solution to a problem which most large observatories face. Big astronomical projects need automated pipelines for data analysis tasks like calibration and imaging. But fully automated pipelines take a long time to develop and require good knowledge of data which is not available at first. So how can observatories still release data quickly to their users after first light or an observatory upgrade? The solution I propose is to use one or more script generators as pipeline prototype. I suggest that this should be done in a three-level development approach consisting of scriptable toolkit, script generator, and finally automated pipeline. I discuss the properties of script generators and finally give a real-world example, the ALMA Observatory, which has used calibration and imaging script generators since 2012. Enjoy the poster and paper.
Hello, I'm Paul Barrett at the George Washington University. I'm the creator of VisFit, which is a Julia programming language package for fitting radio interferometry visibility data. The reason I created this package was because the half dozen applications that are out there I found too limiting. So I developed my own package in Julia, which I consider the successor to Scientific Python. It allows me to analyze radio data instead of several days. With typical software, and within a half an hour typically, I can create light curves and spectra. And it's still in its early stages. It will continue to be developed and should be available on from the Julia Package Manager within a few weeks. If you're interested, please take a look at it, provide feedback. Thank you.
My greetings to all conference participants. I am Olga Zhelenkova from the Special Astrophysical Observatory of Russian Academy of Sciences. For a number of years, we have been conducting massive studies of radio sources obtained as a result of a series of surveys carried out with the Ratan 600-meter radio telescope. For this, we use data from all available resources, sky surveys, catalogs, and so on. We were able to identify practically all radio sources with optical objects. The result is a fairly extensive collection. As we continue to work with these objects, we need tools to conveniently work with the collections. We started developing a prototype information system based on Python and PostgreSQL. Now the system web interface displays images and tabular data. In the future, we plan to develop the system functionality.
I'm Alice Allen, editor of the Astrophysics Source Code Library, and my poster is SciCodes, Astronomy Research Software and Beyond. What if you had a research problem that could be solved computationally, but you didn't have the software that could solve this problem? What if a code that would work for you already existed, but in another discipline? How would you learn about it? That's one problem that SciCodes wants to solve. SciCodes is a new consortium of research software registries and repositories from many disciplines and wants to make scientific software more discoverable across disciplines. This would not only help you find useful research software regardless of which discipline it was developed in, but would also help make your own software more discoverable. Want to know more? Please view my poster, catch up with me at ADAS, visit the SciCodes website, or drop me an email. Thank you very much.
In this video, I will show how to use YAFITS inside Artemix. So let's log in and then search for a source, for example, M83 by source name. And you can see all the different observations that have been done with ALMA. Then I will select one project, for example, this one. You can see for this project code you have here, and most ID you have 10 FITS file, and I can open the FITS file inside YAFITS. And I can select a region here where the signal is. I can do a search to resolve the source and redshift via MED. And then I will display the lines, theoretical line expected, and you can see where are the lines. YAFITS is available via Zenodo. You can download it on GitLab. And if you have any question, please send us an email to artemix@clerma@obspm.fr. Thank you.
Hi everyone, I am Giuseppe Todisco and I'm a research fellow at the Astrophysical Observatory of Catania. I'm here to present the Via Lattea, a visual analytic system that offers a set of tools to study the star formation process in our galaxy. One of the main components is the Via Lattea knowledge base, a collection of datasets and object catalogs. The VLKB offers 2D and 3D surveys, numerical model outputs, and web services for data discovery and data access. The main way to consume the Via Lattea knowledge-based data is through the Visual Analytic Client, an open source application that combines different types of visualization to perform correlation analysis. If you want to know more about Via Lattea, please contact me during the conference. Thank you for your attention and goodbye.
Hi, my name is Lexi, and I am speaking about a tool geared towards web-based polarimetric analysis called Polaris. Polarimetry means measurement of the rotation of the plane of polarized light. It is an important diagnostic tool because from it, astronomers can learn about the magnetic structure of astrophysical objects such as galaxies and the environments they exist in. But polarization properties can vary across a galaxy, and this means that there is a need to examine different interesting areas on the galaxy, which we call lines of sight, in an attempt to get a clearer understanding of the variation of the magnetic field. Astronomers do this by generating various plots of spectra, and that means plots showing variation of magnetic fields at cross wavelengths of each line of sight. To have an overall view, they have to shuffle between the lines of sight on the galaxy's image and their corresponding spectra. But what if I told you that there is a way to visually achieve this on your web browser? Polaris does that. Shown here is what its current interface looks like. Want to know how it works? Please see my poster, scan this QR code to interact with Polaris, and contact me if you would like more information. Thank you.
Okay, and that brings this session to an end. Thank you very much to everyone who attended, whether it is here in this room or anywhere in the world. We have a break now and we reconvene in about 30 minutes time at 12 o'clock South African time, and that is 10 o'clock Universal time. Thank you very much.
Hello, welcome to the last session for this morning event. We'll be starting with a talk by Meg Schramb about exploring Mars with 150,000 Earthlings.
Great, thank you. Hopefully everybody can see this and hear me. I'm sorry I can't be there in person, but I appreciate being able to give this talk remotely. So I'm gonna really be talking about having 150,000 collaborators. I'm not really lying. And so I wanna give a sort of whirlwind talk, an overview of the Planet 4 Citizen Science Project and how we're using human pattern recognition to solve a problem that's been really challenging to solve with computers. But that might change, as I'll show you in my talk. So a lot of times when you hear about Mars, you really think about it being incredibly Earth-like. And we're gonna focus on the bits of Mars that are, rather different. And so on here, you'll see that there's these very dark streaks that are present. And this is an image of the South Pole of Mars. It is, the best way to describe this is it's an area where there's carbon dioxide ice on the surface, and we're seeing these dark fans on the top of the surface, and they appear in the springtime, and there's hundreds of thousands of these. And so we think that they are telling us about the surface of Mars and its climate. So I think it's really important to think about how seems like it took away, but we'll start that again. There we go. Really trying to understand what this process tells us. And so we think is actually happening is that there's carbon dioxide geysers going off on the South Pole. And so we actually think we're seeing that there's a semi-translucent carbon dioxide ice sheet, and that as the sun's light penetrates in the springtime, after the CO2 ice sheet has formed, you get trapped gas underneath a brittle ice sheet. And so, of course, what you expect is going to happen happens. The gas breaks out in any way possible, we think, as carbon dioxide jets. And we think during that process, and again, this ice isn't that thick, it's probably about 1 meter in thickness, probably is bringing up this dust and dirt with it as it moves up through the ice sheet. And that you can kind of see this here in that we see these sort of fans appear right and get further as we go into the spring and late summer. But by the time we get into full summer and there's clearly the temperatures are higher than carbon dioxide ice, we don't see fans anymore. And so it helps us think that we really are seeing what's like a frosted piece of glass, right? That you're looking through. And so you've basically taken some of what's below that ice sheet and put it up to the surface while the ice sheet is there, which is why you see this color contrast in the dark fans, and that once the ice is gone, the material just falls back down and we can't tell the difference. And so you might notice that there's looks like these channels that might look like a spider. And these are dubbed arenaeforms. So we think that they are forming as part of this process of this carbon dioxide jet and seasonal fan depositing process. And it looks like they take eons to form. There are not a lot of images of new arenaeforms forming, but we think it is part of this process that where you tend to find arenaeforms, you tend to find lots more fans coming out of those channels, at least on the surface, although that the arenaeforms are actually below that ice sheet. So again, this is showing you a visual on the side here of what we think we're seeing. And just to give that in a different way, this is showing it in a different schematic. And to prove that this actually can happen, here's going to the Kelso Dunes and putting a slab of carbon dioxide ice down, and you can see that on the edges, it is moving those fine particles. And so we do think that what we're seeing with these streaked features in the South Pole is this sort of fine-grained material that's been brought up by the carbon dioxide gas as it breaks through the ice sheet. And I want to highlight that because these things have directions, we can do things that potentially we've never been able to do, which is actually measure the surface winds of Mars, right? There's only a few things that we've had been able to measure at the surface, and that's usually landers and rovers. And so this is just an example of the different types of measurements that have been made, from pressure measurements from Viking to actually sticking plumb bobs on Phoenix to measure wind direction, or watching which way the clouds are moving with some of the rovers. And so we don't have lots of areas on Mars that have wind measurements, unlike the Earth, right? Which is how we improve our global climate models. And so we think that these fans really are showing the wind-blown direction. Here's just showing 2 example images from the HiRISE camera on Mars Reconnaissance Orbiter. And just see here that these fans are bifurcated in a couple different directions. And so we think that is, again, telling us about that the wind direction changed as the material was venting out. And then on the right, you see that these look very much like, just spots maybe where the jet is coming up and then just depositing material below. So we think that this is, again, something that can tell us about wind direction by looking at where we do see directionality and how it's changed, and also how we see possibly where there are no directionality, and that's maybe telling us that the wind wasn't strong enough to blow this material. Also, the thing that this is all being driven by a sublimating ice sheet. And so Mars is a red planet. There's a lot of red dust in the atmosphere, and that also is a part to play. And so this ice sheet is semi-translucent. It is like frosted glass in that sense of it does have these particulates in it, embedded within it. And that may change how things outgas. And so just an example here on the left and the right are 2 different monitoring seasons from the HiRISE camera to Mars Reconnaissance Orbiter. And it's the highest resolution camera we've sent to Mars, but it also had the luck of coming right before a large global dust storm obscured the entire surface of Mars. And during that global dust storm, actually, is when the seasonal South Polar Cap was forming. And so that carbon dioxide ice that was being formed and deposited out of the atmosphere, it's about 30% of Mars's atmosphere, thaws out or snows out to form that seasonal ice sheet. That had the dust storm, which had so much dust in the atmosphere, you couldn't see down to the surface for weeks. And so this on the left is season 1, that's before the dust storm. And over here on the right is season 2, that's post dust storm, with the ice sheet that had the enhanced amount of dust within it. And so clearly you can see by eye, there's some differences. There's a lot more seasonal fans in season 2, right, in that ice sheet that has a lot more dust in it. So again, we think that by measuring the number of fans, how much the surface has changed in terms of albedo as we create these seasonal fans, probably is telling us something about this ice sheet and the Martian climate and how it responds, the Martian climate responds to these global dust storms. But you really need to actually measure all of this and say how much area has been covered, and that actually has been tricky. So you might argue this should be an easy machine learning problem, and it's apparently not. So the HiRISE team has tried this for a very long time, but this is just showing you a smattering of images from HiRISE in different colors. And again, HiRISE is the highest resolution camera ever sent to another world. It can see a coffee table sized object on the surface. And you can just see here, there's a lot of colors and textures. And so while I'm talking, you probably easily spot where these are the dark fans and identify those separate from the spider channel features. But this is really difficult to make machines do, because this is these features are very, they're not sharp boundaries. And so that has made it very hard for any machine learning that's been thrown at this without having a large training set. And so part of the problem is to create a large training set. The problem when there's hundreds and thousands of these features. Getting the team to even mark a few hundred subframes of a HiRISE image took months. So this is, when there's hundreds of thousands of these fans, we're kind of stuck in we don't have a training set yet to use machine learning on, and other automated techniques we're not doing as well as what people could do by eye. So that sort of led to this process of joining with the Zooniverse. And so I'm showing you on the left, the Planet 4 science team, the Zooniverse team, and really highlight that Zooniverse is the largest platform for citizen science, for online citizen science in the world. And it really enables being able to go and in their platform, I highly recommend go taking a look, but with their project builder tool in 30 minutes, you can have, or less, you can have your own citizen science project. You might be arguing more over what task you want rather than actually being able to set it up. And so I think that's one of the powers of their platform now and what they've grown into. And so I'll highlight the fact that we partnered with them to solve this problem by asking people to mark these fans. And so we have 30 people look at a HiRISE subtile. It's about 800 by 600 pixels. And so we ask people to go and mark with the ice cream cone feature, the directions of the fans and blotches, because we care about the directions for the wind when we want wind measurements, and we care about getting as many of the features as possible to figure out how much material was outgassed, again, to look at that, how things change, right, with that ice sheet and its properties. So you can go to planet4.org. We're live with data now if you get bored in this talk. But the idea being is that we actually can combine those classifications of what's known as the wisdom of crowds. So this has been around for a while. If you've heard of Galaxy Zoo, it's exactly the same thing. We just have a little bit more complication of that these are actually more spatial features. And so we apply a sort of a pipeline and a classification scheme that takes using clustering effectively to cluster these sources. And so all we're doing is clustering the positions of the fan and blotch drawings of 30 people look at each image. And so we take their individual classifications and we combine them together. And so then if there is a fan feature and a blotch feature, because we cluster them separately, we figure out where they're overlapping. And then based on the majority vote, we decide whether the feature that these people marked is a fan or a blotch effectively. And then we're going to ground project that. And so all we're doing is sort of going through this process of figuring out what our fans and blotches are, and then looking at whether, where they overlap, which one we believe more. And again, we have data that you can choose that if your definition is different than mine, you can go back in our data and create the best sample that you want. So, I'll show you here. It's detailed in A&L 2019, but the idea being is we take the base positions, that edge of that ice cream cone, and the center of the ellipse, and we use that to basically cluster with looking at some of the angles and positioning, mainly for the ice cream cone feature, but also for the ellipse. And then go through looking at the overlapping features. And so by doing this, we're not looking at one person, we're taking the majority effective vote. And so for us, we say that if any feature, if 50% or more of the volunteers identify it as being a fan, then we keep that as a fan. And again, it takes at least 3 volunteers to have marked the same feature for us to identify it as being a source. And so we've gone through and used this pipeline and been able to take all of our classifications, use that wisdom of crowd effect, and be able to actually create a catalog of these seasonal fans and blotches, the largest that's ever been produced for looking at Mars and these features. So I just want to highlight that proof's in the pudding. I can tell you that works, but I should be able to back that up. And so let me just show you here. This is a sub image from HiRISE. Again, this is one tile, we call it in Planet 4, that we had volunteers mark. And so in here, you'll see these are all the fan and blotch marking. This is rather all the fan markings from the volunteers. Different color represents a different volunteer. And then over here, that image next to it is all the blotches. Again, different color, different volunteer. And so again, the same sources are identified, right, as both with a blotch tool and a fan tool. And so when we use our clustering, again, treating these separately for the moment, we get this image down here and this image down here, again, identifying most of the features. And then we look at the majority vote and see how many volunteers drew the fan versus the blotch, or contributed to the final clustered, fan features and blotch features. And so at the end, we get this here. So overall, we're getting all of the features in just this example, right? We're getting directionality, and also occasionally we'll also get, a mixture of identifying these features as fans, but also, again, if there's a larger feature marked, in this case, a lot of people were drawing circles around all 3 of these, that will pop up as well. So we've been able to use this catalog to basically now be able to look at directionality and understanding how this can tell us about the Martian climate. But before I get into that, again, I want to show more proof of the pudding. And so this is just taking a random HiRISE sub-image and showing you here this rose diagram, which is telling you which way we think from our catalog the fans are pointed. And so again, we think they're pointing from sort of bottom right corner to top left. And again, you see that here, that these fans are mostly going in that direction. Okay, so I showed you a couple plots. You might not argue that that's proof. And so one of the things that has been taken a lot of time is to prove that this volunteers combined assessment is as good as the experts. And so here I'm just showing briefly, these are 3 of the science team. Here's me, so you can see how bad or good I am compared to the catalog. But the idea is we've taken a random about 200 of these tiles. So again, sort of an image like this, and had the science team mark them. And so we're individually in blue, and the catalog is in orange, and we have number of fans plotted versus the fan length. And so overall, the variation between all three of us is the science team is that we don't agree 100%, right? We vary amongst ourselves in terms of our analysis. And so, but overall, even with the catalog, there is some variation, but it's very similar to the variation between the three experts. And so the highlight and point of this, and the paper goes through into way more detail, is that the catalog is just as good as us, as on the science team marking this, and they got it done way faster. It took months to get even just 200 images, and we have thousands of images on the site that people are analyzing. And so on the right, I can show you, that's looking at fan lengths. Well, what about directionality? And so here is looking at a histogram showing the difference if you take the average direction of these fans and these small sub images, and you compare what the expert had for that image versus the catalog, and we're matched within about 10 degrees. And so we think that's pretty good proof that combining the assessments of multiple non-expert volunteers, in this case, with this online citizen science project is getting us results that we can actually use for science. So at the end of the day, what we've gotten out of this is that we've gotten 160,000 fan measurements and 250,000 blotches effectively identified, which means we have directionality and we have the ability of knowing their shapes and locations to be able to look at how much of the ice sheet gets coated in a darker albedo. And so again, this was roughly 43,000, these sub-images that were reviewed by volunteers. And so that's how we're, get our 150,000 volunteers, right, are coming from people looking at these images. And again, each image getting about 20 to 30 classifications or individual assessments. So the tiles are coming from about 221 high-res images that we looked at over 2 Martian years, covering about 28 regions of Icarus on the South Pole. So this is the power of this, is that we're able to get really into the meat of being able to look at different regions because we've had the ability to process this data so quickly. And, again, there's still we now have a set that we could use for machine learning or automated routines. And I'll really touch on them briefly at the end. But here I'm just showing you the different locations or regions of interest that HiRISE had looked at for those 2 Mars years. And here is just showing you Alcibiades, or season on Mars. Basically, its location and its orbit around the sun, but it tells you about season. So we're starting here in southern spring and going to southern summer. And here we're showing it in latitude. And just showing you Mars years 2, the season 2 and season 3, the monitoring campaign. And all I want you to get out of this is that we cover a wide range of latitudes, and that there is very good seasonal coverage. And here is a safe mode event by our poor spacecraft not being able to observe. But while this spacecraft is observing, we've been able to get data pretty frequently. So now what we have the beauty of doing from having these classifications is actually able to look at how the wind direction has changed over time. So on the top, I'm showing you Mars year, that season 2, and showing you early spring and sort of late spring, breaking that the wind directions into, and doing the same for the same region, blocked into the next year, into early spring and late spring. And all I want you to get across here is that by having all of these individual measurements, what we actually can start seeing is that the wind started over here and has been slowly marching over to this side. And so that we're actually now starting to see proof that the wind directions are changing. And that if they were actually, the fans are being continually renewed in the same directions, then we'd actually see lag of seeing these features here and remain here, right, for a while as we kept moving. And you'll see that these colors represent the different images at different times, and that is very cleanly, we see the various early spring image, and that directions are gone as we move over to the next ones. And same thing in late spring, you don't see any of the fans that are over in this direction. So we've gone from being really data poor to being data rich. And so I'll highlight just some of the brief results that have come out in our latest paper, sort of have this ability to having so many volunteers looking at the data and combining it together in ways we couldn't do before. So one example here is showing a region we've dubbed Macclesfield. And so we're showing the fan direction here versus the fraction of the total number of fans in the image. And then on the second plot is showing the fan length. And again, that fractional coverage. And so this is the sort of season 2, and this is season 3 of those 2 campaigns. And all I want to get across is that, you can actually see the winds bifurcate here as we go from early spring all the way down to late spring. And each one of these plots is for a high-rise image where we've had those catalog markings right from Planet 4. And so again, you can see season 2 and season 3 have differences, but we can see that the winds actually bifurcated much earlier here in season 3. So we don't fully understand what's going on, but we actually now have this really important starting of wind measurements, right? And directionality on the south pole of Mars over a wide range of latitudes and longitudes. And so what we're getting into is actually starting to compare and trying to understand what is the wind directions actually telling us by comparing to climate models. And so we're using MRAMS, which is a modeling system that puts down a high resolution grid down on the South Pole. So this is just showing a schematic of that on the left and right. This is the larger grid, and then nested within that is higher resolution grids that is using as good a topography as we have. And each one of those dots is one of the locations where we have high-rise measurements and have Planet 4 catalog. So I'll just wrap up by showing a couple of results and then touch briefly on machine learning. And so what I want to highlight is that, you know, one of these regions called Giza, we see that the wind directions are clearly changing. And that, again, we're seeing a little bit of what's going on as we go through the season. But we can compare that to the model. And here's actually showing three Mars days, because the model is so complex and takes so long to run that effectively, even after weeks and weeks and weeks, we get 3 Martian sols. They're each different, but what I want to highlight is that we're plotting the sort of season on Mars down here versus the directionality. There's also, each plot tells you about speed individually, but each one of these is a different snapshot of season from early spring to the start of summer. And all I want to get across is that each one of these red lines is telling us a Planet 4 average measurement of the wind direction. We can look at speed, but there's some uncertainty because we have to estimate particle size from orbit. But what the model is showing in blue is where it thinks it gets wind directions from the upper atmosphere and rather the lower atmosphere, and black being the higher atmosphere. And all I want you to get across is there are times when our wind directions at least match with the model. If there is some wind produced by the model at the surface that could be producing what we see from the fans. And so I think that's exciting that for the first time, we're actually able to take these observations and sort of match the fan directions to a model. And we at least can say, overall, it's fairly consistent. There's some blaring, issues sometimes, such as we have measurements down here, and this day doesn't seem to represent that, but these other 2 days from the model do create that sort of the location for those winds. So again, this is sort of, maybe we're at the crude step and we can look at another area and again, see something similar that we're seeing, again, that directionality, where the fans are directed, right? The expected wind direction we would take out from what would need to produce those, we seem to be able to create in these climate models. And that we're also starting to see where climate matters and where topography matters. And so this is just showing basically an evolution, a topography map, and showing our Planet 4 wind directions on top of it, and showing you those 2 regions. So you can see here from Manhattan, all I want to get across is that there's a valley in here, and that's clearly driving lots of the dynamics in the winds. And we still do pretty well in mapping what we see on Planet 4 to that climate model. So it seems like what we're getting in terms of the wind measurements and sort of the broad strokes of these weather models is that they're matching. And that although we have the really high resolution imagery, the topography that's going into these models isn't very high resolution. And so it seems like it's the bulk features right now of the topography that are driving the katabatic winds and the dominant winds. So this is the first time we've actually been able to measure for a large area of Mars these wind directions from citizen science. Perfect. And so what I'm going to end with right now is really just talking about machine learning, and that we've just started to be able to look at machine learning, and what we're finding is that certain clustering techniques don't work. CNNs are okay, but what they've failed to do is actually get directionality. So every machine learning expert that we've worked with has failed to get directions of the fans' blotches. What they can do is find them. And so the best we've been able to do so far in a paper we just submitted to Icarus is basically have a CNN that can, sort of one of these neural networks that is actually able to identify from the Planet 4 catalog, being trained on it, where the sources are. And so here, just to show you that, I'll go back one. Here is to show you that on the left, you've got in the small image, you've got the Planet 4 catalog, and on the right is the CNN. And it does pretty good, at least identifying the sources. But overall, right, when we look at these techniques, and this is too showing in the left plot is showing the difference between recall and precision for this clustering algorithm that was tried, this automated model, as well as the CNN. And so all I want to show here is that we want to be up in this corner, right? That precision is telling you what, out of the stuff that you found that you predict to be real or fans, how many of them are actually real fans. And then same thing, recall is telling you about sort of on the opposite side, right? It's telling you about out of your actual positive data, how many times you got that right? Right, and you want to be in the top corner here. And so these are each different locations on Mars that we had high-rise imaging in. And so most of the time you get into this corner. And again, the larger dot is just saying it had a better value for the DICE, a DICE metric that it was using, coefficient was using to, again, look at another way of looking at how well the machine learning algorithm was doing. So clustering didn't do as well. It often got confused, which is why it's more down here. But we did in several cases get into that corner for the CNN. So it's still not good at actually getting directionality. So we still need people. So I'll say, just to wrap up, is that Planet 4 relaunched on the News Universe Project Builder platform last year. So it's continuing to go strong. We still have lots of data to get through, and we need more data to be able to identify these seasonal fans and blotches and get directionality, because we still yet don't have a machine learning algorithm or an automated way to identify directionality yet. It's also spawned several other projects, which we now keep all together at planet4.space. Some of them have data right now, some of them don't. But I'll leave up my conclusions, and I'm happy to take any questions. So thanks very much.
Thanks, Meg. Thanks, Meg. We've actually got quite a few questions on the live questions. The first one is by Peter Teuben. Are you keeping track how long users typically endure doing this tedious work? What's their attention span, in other words?
It's as much as the regular internet. So typical values for this universe are about the same as people's attention on Wikipedia. So most people do a few. About 80% of the classifications are done by 20% of the volunteers. Our task is harder. So we definitely see that there's less people doing hours and doing it for long periods of time. I haven't looked in a while, but it's the typical average span of a human being on the internet. So it's very quick, it's minutes. We're lucky if we get longer than that.
Right. Are more seasons planned by Kathleen Laborie? I'm not sure whether we're talking about observations or about analyzing the observations, but it looks like you got much more data to sift through. So
yes, so as long as HiRISE is still observing, they do a seasonal South Polar campaign each year. So we've gone through about 4 seasons now. And we're processing more. So we're sort of science team limited now, which is great to be in. We need more people, I think, to work on the data interpretation of the data. But yeah, we've now reached launch site, and we're working on getting through the next several seasons. So knock on wood that HiRISE is the only camera that really can see these fans and blotches in that much detail. So there's no replacement for it right now. So we hope it hangs on for another decade, or if it can.
Okay, then there are a few, we don't have an awful lot of time, so I'll defer, some of the questions about how you credit the contribution of 100,000 Earthlings in your papers to the dedicated channel. But I'll ask this question about from Michelle Lochner, who just came through, which I think is interesting. Since I'm into anomalies, was there any flexibility in the interface for users to indicate anything weird they find, which is neither a fan nor a blotch?
Absolutely. In the old version, we had something called interesting. And it was that they could put a star on anything. And we found that they didn't use it very often because they didn't know what to put. And so although it's fine to give something like that, I think what we found is that you have to help people figure out what is interesting or what is an anomaly for them to understand it. So for us, we didn't get much out of that interesting feature. but the discussion tool helps with that. There's a discussion tool with all of these. And that sometimes we could get people talking about it and they could add their own hashtags or labels. And that helps because then they can describe something in their own way. So, but in the interface, we couldn't find any anomalies very easily with the classification interface. Is interesting feature. So we actually dropped that in the newest version of Planet 4.
Mm-hmm. Thanks. There are a few more questions that I'll defer to the dedicated channel, but I think we need to move on. Thanks again, Meg. I mean, that was extremely interesting for us Earthlings.
Thanks.
Okay, so for the next and last talk of the session, we've got Valentina Cesare connecting remotely, I believe, and she's going to be talking about Gaia AVU GSR parallel solver towards the exascale infrastructure.
So, hi everyone, I start sharing my screen. Can you hear me well?
Yes. Very.
So, good afternoon, everyone. I am Valentina Cesare from the Astrophysics Observatory of Catania, and during this talk I will present the Gaia AVU-GSR parallel solver as an example of big data application that exploits exascale infrastructures in astronomy. During this talk, I will first introduce the ESA Gaia mission, then I will present the Gaia AVU-GSR parallel solver, and I will talk about its porting on a GPU environment. Then I will present the performance tests of this code, and at last I will draw my conclusions and present the future works. The main target of the Gaia AVU-GSR solver is to derive the positions and the proper motions of about 10 to the 8 stars in our galaxy observed with the Gaia satellite with a precision and the microsecond level. So now I spend a few words about the Gaia mission. The mission was developed by the European Space Agency and it was launched on December 19th of 2013. The mission was initially scheduled for 5 years, but it is extended so far to 2022. The third early data release of the mission was published last December, and the main objective of the mission is to make astrometry, namely to map the positions and the velocities of the stars in the Milky Way, to investigate its origin and evolution, and to test different theories of gravity. The Gaia AVU-GSR solver is developed under the Gaia Data Processing and Analysis Consortium, or DPAC, which is a pan-European collaboration that involves 450 scientists and engineers from across Europe. The DPAC is organized in 9 coordination units, each one responsible for a portion of data processing challenge. In particular, the third coordination unit is responsible for ensuring the accuracy of the data collected by Gaia, and in particular of the AVU-GSR pipeline. Specifically, the AVU-GSR module, where AVU-GSR stands for Astrometric Verification Unit Global Sphere Reconstruction, aims to verify the main solution found for the Gaia mission, which is called the Astrometric Global Iterative Solution, or AGIS. The main challenge of this process is the big data flow that we receive every day from the satellite. Specifically, we receive 50 gigabytes of compressed raw data per day from the satellite to be processed. I now talk about the structure of the AVU-GSR solver. The solver is the most computational demanding part of the AVU-GSR software collection, and its core computes the solution of a system of linear equations that has this structure. In particular, the coefficient matrix of the system A is large, having a dimension of about 10 to the 11 times 10 to the 8, and sparse, since the majority of its elements are equal to 0. Having a matrix with such a dimension implies a big data problem that can be partially solved by adopting during computation a matrix with only its elements different from 0, namely a dense matrix, which has a dimension that reduces to about 10 to the 11 times 24. The unknowns of the systems can be divided in astrometric unknowns, where we have 5 unknowns for each of the 10 to the 8 stars in the Milky Way, the attitude and the instrumental unknowns for the Gaia satellite, and the global unknown gamma of the parameterized post-Newtonian Ramondt formulas to describe the space-time. Since the number of equations of the systems equal to the number of observations of the stellar parameters is much larger than the number of unknowns, the system has to be solved in the least square sense. Specifically, we solve the system in an iterative way with a modified version of the preconditioned LS-square algorithm that computes at every step the approach mode 2 function and the approach mode 1 function that evaluates the vectors of residuals to be minimized. The LS-square can be represented with this scheme, and it is made of a while loop that calls at every step the approach 1 and the approach 2 functions. The iterations are stopped when either a convergence condition or a maximum number of iterations set at runtime are reached. The code is parallelized with MPI plus OpenMP, and this scheme represents the parallelization of a single node of a computer's cluster of the system of equation. In particular, this represents the run on 4 MPI processes. Each colored portion represents the computation assigned to a single process. The data are uniformly distributed among the processes to reduce the total number of MPI communications. And we assign to a single MPI process an horizontal portion of the coefficient matrix A, namely a subset of the total number of observations. Moreover, the observations in a single MPI task are further parallelized over the threads of OpenMP. I now talk about our main work, namely the porting of our application on a GPU environment, which is part of a paper that is in preparation. To further improve the performance of our code, we decided to port it on the GPU by replacing the OpenMP paradigm with OpenACC. We test this code on an NVIDIA Volta V100 GPU with 16 GB of memory, in particular on the Cineca supercomputer Marconi 100, which has 4 of these GPUs per node. Parallelizing this kind of system on about 10 to the 2 more cores than on the CPU is ideal for big data computation. And in particular, our application runs on multiple GPUs, according to the number of MPI processes set at runtime. This scheme represents the parallelization of the systems on a cluster with multiple nodes. In particular, here we consider the parallelization on 4 nodes, where each node is represented by a big stripe divided by the black solid line, and where we run on 4 MPI processes per node, where each MPI process is represented by a small stripe. We can see that the computation assigned to a single process is assigned to a single GPU. And in particular, on a system like Marconi 100 that has 4 GPUs per node, running with 4 MPI processes per node would be optimal, since we exploit the maximum number of GPUs per node. In GPU parallelization, it is important to correctly deal the data transfers, because a bad management of this movement can cancel the advantages provided by parallelizing on a large amount of cores. In particular, we have to try to minimize these transfers. In this pseudocode, I highlight the directives that manages the data copies. And in particular, we move about the 95% of the data from the host to the device before the starting of the entire square algorithm. And this is possible because these quantities are not modified during computation on the GPU. Instead, we move only the 5% of the data from the host to the device and to the device to the host at each iteration, both from the prod 1 and for the prod 2. And these quantities are the unknown vectors and the known terms vectors. But these movements, despite they are made at each iteration, does not significantly affect the code performance, since they only represent the 5% of the data. We ported with OpenACC both the approach mode 1 and 2. For brevity, I only show the astrometric section for each mode, since the other 3 sections, the attitude, the instrumental, and the global, follow the same structure. In the approach mode 1 is organized in 4 parallel regions, each one for each section, introduced with the Pragma ACC parallel directive, where the most external for loop is parallelized with the Pragma ACC loop directive, and the external for loops iterates on the number of observations in each MPI process. Instead, the approach mode 2 is organized in a single parallel region, where again we parallelize the external for loop, and where we put this Pragma ACC atomic directive to prevent different threads of the GPU to write the same element of the unknown vector x. We compare the performances of the OpenMP in blue and of the OpenACC in red codes on Marconi 100. To run this performance test, we simulated a system of stars, setting the parameters of the system such to achieve a given amount of memory. In particular, we ran the test on a single node of the clusters on an increasing number of MPI processes with a memory fixed to 10 GB, and we ran 2 tests on an increasing number of nodes of the clusters, both with a fixed memory to 40 GB and with a memory proportional to the number of nodes, in particular 40 GB of memory per node. And in both tests running on an increasing number of nodes, we set 4 MPI processes per node. We can see that in every case, the OpenACC application is faster than the OpenMP1, and in particular, we achieve a gain of about 1.5, which is about constant when the OpenACC code runs on the maximum number of GPUs per node, which is achieved when we run a number of MPI processes larger or equal to 4. In passing, we also noticed that we also verified in the proportional memory test that the weak scalability is verified both for the OpenMP and for the OpenACC codes. So to conclude, in our final run, which will involve about 10 to the 11 observations and 10 to the 8 stars, we would expect that the OpenMP code would run for about 30 days. But with the OpenACC code, where we achieve a gain of about 1.5, the run would last only 20 days, and we would save about the 33% of the time. With this kind of gain, we can state that the code is ready to enter in production and to run on pre-exascale infrastructures like Leonardo that will be launched in Cineca in 2022, and that have GPUs with a larger memory and a higher GPU over CPU ratio with respect to Marconi 100. And running this same code on this kind of architecture would imply an even higher gain with respect to the current one. Talking about the future projects, about OpenACC, we would aim to eliminate the residual data copies at each iteration of the LS² algorithm of the known terms and of the unknown vectors. But our main target is to port the code with CUDA, which is scheduled by the first quarter of 2022 by parallelizing the code following the architecture, the GPU architecture that will be on Leonardo. And with this porting, we aim to obtain a much higher gain in performance with respect to the actual one. So that's all. I thank you for your attention, and now I wait for your questions.
Thanks, Ellen. Thanks, Valentina. Very important considerations for future HPC projects. I don't see questions on the live questions channel. I'm going to ask one. So is this new code being used in, in operations, I mean, in the Gaia data reduction, or is this a test that you've been carrying out in order to then streamline it and apply it, I mean, to the main Gaia data reduction task? I don't know how that's parceled throughout the consortium.
It is still not implied for the Gaia data reduction. Now we are running on simulating systems, but it will be in production soon.
I see. Thanks. There's a question being typed, so let's give the writer a couple of seconds, unless somebody in the room would like to ask one. There's now 2 people typing. Let's give them Okay, so we got one question, which is from Ulrich. Why is the parameter space so sparse with the parameters reducing from 10 to the 8 to 24?
So the coefficient matrix, we receive this kind of the coefficient matrix with the data scheduled like this, and we did not set the structure of the coefficient matrix, and it is due to the satellite. We receive this information from an external source, but it is important that for example, for the computation, the astrometric part is organized, yes, with sparse structures, but which follows, for example, a block diagonal structure. And for the attitude set, we have also the parameters organized in different blocks. But yes, to accelerate, we adopted an ad hoc compression algorithm to only consider the parameters different from 0 during the computation. And concerning the previous question, the OpenMP version of the application is already in production, and it is already implied with the task of Gaia.
Excellent, thanks. So, well, there's other questions that we will have put up on Discord. Let's thank Meg and Valentina again for their talks, and I'll leave it to our illustrious leader to discuss the practicalities of the group photo.
Right, so we were supposed to gather for a group photo now, but the photographer tells us that the informal photo we took just before this has come out so nicely that we don't need anything else. Oh. So all the in-person participants are free to go to lunch now. For the virtual participants, I'd like to announce that we are going to do a group photo in GatherTown, and we're going to have 2 sessions in GatherTown, one at 10 p.m. tonight, so that's after the last talk of the session tonight. And then there's going to be another session tomorrow morning at the start of the second morning break, the long one. So if you could all please gather during those times in GatherTown, get into the venue, head out south from the venue until you see the beach, and there's a giant ADAS logo on the beach, so you can stand around on the logo. You don't have to form ranks or anything, it's also informal. And just mill around there for like the first 10 minutes of those 2 time slots, and we'll get some screenshots. And in-person participants, you can do this as well, too. As long as you leave a browser window open, your avatar is going to be represented on the beach, and you'll be in the photo. I've also posted this in the announcements channel on Discord, so you can refer there for details. Thank you very much.
Hey, ciao.
Jordan just texted me he wants to come for lunch, late lunch, but to have a lunch.
Oh, yeah, I wasn't on.
Yeah.
So.
No, you said something it would be nice if us could join as well, but very spontaneous.
Well, it's late.
He's home, yeah.